For more than 50 years, the Moon has been waiting. The last footprints left in its dust were made in 1972, when Apollo 17's crew climbed back into their spacecraft and began the long trip home. Since then, generations have looked up at the Moon, wondering why humanity walked away after such a giant leap. Now, the Moon is calling us back. NASA is preparing to send astronauts once again, but instead of short visits, the goal is to build, to stay, and to use the Moon as a stepping stone for the future. Rival nations, private companies, and entire alliances are also turning their eyes to the lunar surface. The next few decades may transform the Moon from a silent witness in the sky into a bustling frontier. The dawn of the space age and the Cold War rivalry. On October 4, 1957, a small beeping signal was picked up by radio operators across the globe. The sound came from Sputnik 1, the first artificial satellite to orbit the Earth. It was no larger than a beach ball, weighing just over 180 pounds, but its presence in the sky carried a weight far greater. For the first time in history, humanity had sent something into space, and it was circling high above every continent and ocean. The world had entered a new era. The space age had begun. The Soviet Union's launch of Sputnik stunned not only the general public, but also scientists, governments, and militaries worldwide. Until then, space had been something distant. Suddenly, it was no longer a dream, but a fact. The satellite's steady signal, transmitted in short bursts, was a constant reminder that human technology had broken free from Earth's grip. For the United States, it was a moment of shock and even embarrassment. The Soviet Union had achieved a milestone that America had hoped to claim first. In the midst of the Cold War, when prestige and influence were tied to technological progress, the launch carried political and cultural consequences that went far beyond science. Families stepped outside into the cool October nights, looking up at the stars in hopes of catching a glimpse of the tiny moving light. Newspapers ran stories about the satellite, and radios played recordings of its signal. Some people celebrated the achievement of science, while others grew anxious. If a satellite could reach orbit, could a nuclear warhead be placed there too? The Soviet Union quickly followed Sputnik 1 with more bold demonstrations. In November 1957, Sputnik 2 carried a living passenger, a dog named Laika, into space. Though Laika did not survive the mission, her flight proved that living creatures could be launched into orbit. This step was vital for the next great leap, sending a human being. The United States scrambled to respond. Early attempts to launch satellites failed, with rockets exploding on the pad or breaking apart in mid-air. Each failure was broadcast around the world, magnifying the sense that America was falling behind. But success eventually came in 1958, with the launch of Explorer 1, America's first satellite. It carried scientific instruments that discovered the Van Allen radiation belts, showing that space could be studied in ways no one had imagined before. That same year, the United States founded NASA, the National Aeronautics and Space Administration, a new agency dedicated to leading the country into the future of space exploration. While America reorganized, the Soviet Union prepared its next daring step. On April 12, 1961, a rocket lifted off from Baikonur Cosmodrome, carrying a young Soviet Air Force pilot named Yuri Gagarin. Within minutes, he became the first human to leave Earth. His spacecraft, Vostok 1, circled the planet in a single orbit lasting about 108 minutes. Gagarin's voice crackled over radios, reporting on his journey, while millions followed the event with awe and disbelief. He returned a hero, not only in the Soviet Union, but around the world. Gagarin's flight showed that people could survive the stresses of space travel, endure weightlessness, and return safely. His calm words and smiling face became symbols of hope and pride. At the same time, his flight was also a demonstration of Soviet power, proving to the world that they were leading the technological race. For the United States, it was another wake-up call. The American response was swift. Just weeks after Gagarin's flight, President John F. Kennedy stood before Congress and declared that the United States would land a man on the moon before the end of the decade. It was an audacious promise, one that pushed the limits of technology, engineering, and human imagination. The announcement turned space exploration into a clear contest of will and capability. Governments invested enormous sums of money into research, developing new technologies that would not only serve the space race, but eventually filter into everyday life: computers, satellites, telecommunications, and more. Behind the scenes, the competition was intense and often secretive. Engineers and scientists worked long hours, knowing that each success or failure would be measured not just in technical terms, but in political meaning. Every launch carried risks, and every astronaut or cosmonaut who climbed into a capsule faced dangers that were only partly understood. Yet the spirit of daring was powerful, fueled by the belief that humanity was on the edge of something monumental. In the tense climate of the Cold War, the space race became a symbol of national power and global influence. For the Soviet Union, the early victories in space were powerful propaganda tools. They showed that communism, often dismissed in the West as rigid or inefficient, could achieve feats once thought impossible. The Soviets made sure the world saw their achievements as not only scientific, but political. When they placed the first satellite in orbit, then the first living creature, and later the first man, each event was presented as evidence that their system was ahead of the West. In the United States, these triumphs caused both fear and determination. The launches were reminders that the Cold War was not just about armies or nuclear weapons. It was about winning the confidence of allies and the admiration of nations still deciding whether to align with East or West. If the Soviet Union could conquer space, then perhaps their political model would seem stronger to countries in Africa, Asia, and Latin America. The American government understood that losing the race for space could mean losing influence across the globe. As a result, money and talent were poured into new programs at an astonishing pace. NASA grew rapidly, hiring thousands of engineers, scientists, and technicians. Entire industries shifted their focus toward developing new rockets, spacecraft, and support systems. Universities expanded their programs in physics and engineering, training a new generation of specialists. Billions of dollars were committed to space exploration to prove that democracy and free enterprise could achieve more than the Soviet Union's planned economy. The rivalry created an urgency that curiosity alone might not have inspired. Before the Cold War, some scientists had imagined sending people into space, but progress was slow and funding limited. The competition changed that completely. Every year brought new goals and deadlines. Each nation was determined not to fall behind. The result was an acceleration of technology that might otherwise have taken decades. The moon quickly became the ultimate prize. It was close enough to reach with the rockets of the time, yet distant enough to represent a great leap. Landing a human on its surface and bringing them safely back would require enormous skill and resources. It was a goal that would clearly separate the leader from the follower. For the Soviets, who had claimed the first milestones, reaching the moon first seemed a natural continuation. For the Americans, who had suffered a string of early setbacks, it was a chance to overtake their rival and regain the initiative. President Kennedy's announcement was a public promise, one that tied America's reputation to the success of a single project. The Apollo program became a national mission, absorbing vast sums of money and the labor of hundreds of thousands of people. Factories across the country produced parts for rockets. Laboratories designed new materials and tested new systems. Astronauts trained their bodies and minds for missions no human had ever attempted. The Soviet Union was not idle either. They developed powerful rockets, tested new spacecraft, and sent cosmonauts on longer and more complex flights. For a time, they seemed to hold the advantage. They completed the first multi-person crew mission, the first spacewalk, and the longest duration flights. But their efforts to reach the moon faced difficulties. Their largest rocket, the N-1, suffered repeated failures, never achieving a successful launch. The Americans, with their Saturn V rocket, eventually gained the upper hand. The pace of advancement drove technology forward for all of humanity. Satellites launched for political reasons ended up transforming communication and weather forecasting. Rockets built to carry national pride into space later inspired commercial uses and scientific missions. Even though the rivalry was fierce, the results reached far beyond propaganda. The triumph of Apollo. Apollo was, at its core, a gamble. The challenges were staggering. Rockets of unprecedented size had to be built. Navigation systems capable of guiding astronauts 250,000 miles away had to be created. Life support systems that could sustain humans for over a week outside Earth's atmosphere had to be tested. Even small details, like how astronauts would walk on the lunar surface without falling, or how lunar dust might affect machinery, were unknown. To commit to such a goal with no clear path was an extraordinary risk. Yet it was also a statement of faith in American science and industry, as well as in the determination of its people. What followed was a mobilization on a scale rarely seen outside of wartime. By the peak of the Apollo years, more than 400,000 people were directly involved in the effort. Universities received funding to train a new generation of specialists, and contractors across the country were tied together in a vast web of collaboration. The need for smaller, more reliable computers drove progress in electronics. Advances in materials, science, life support systems and communications were accelerated. Over the course of the 1960s, the Apollo program consumed billions of dollars, eventually becoming the most expensive peacetime project in American history up to that point. For some critics, this spending seemed wasteful at a time when poverty, civil rights struggles, and the war in Vietnam were pressing issues. The program also transformed the nation's sense of possibility. Each step forward in Apollo was broadcast to the public, turning astronauts into national heroes and launches into shared spectacles. Families gathered around television sets to watch the fire and thunder of the Saturn rockets lifting off. Children followed the missions in classrooms, drawing pictures of astronauts and lunar landings. The sense that America was pushing the boundaries of what humans could do brought pride and hope, even as the country wrestled with divisions at home. The scale of Apollo meant that the risks were ever present. The Apollo 1 tragedy in 1967, when 3 astronauts died in a fire during a test on the launch pad, showed how dangerous the undertaking was. The loss shook the program and forced painful changes, but it did not stop it. Instead, it strengthened the resolve of those involved. The gamble worked in ways few could have predicted. As the decade wore on, each Apollo mission brought the United States closer to fulfilling the promise. The Saturn V rocket, a machine taller than the Statue of Liberty and more powerful than any rocket before it, became a symbol of American engineering might. Training missions in orbit tested docking procedures, life support systems, and re-entry techniques. Each step carried immense pressure, because the world was watching, waiting to see if the gamble would pay off. By the time Apollo 11 launched in July of 1969, the program had already demonstrated that it was possible to send astronauts around the moon and return them safely. Yet the landing itself remained a risk unlike any other. The crew consisted of 3 men, Neil Armstrong, Buzz Aldrin, and Michael Collins. Armstrong, the commander, carried the responsibility of being the first to step onto the lunar surface if all went according to plan. Aldrin, the lunar module pilot, would join him there, while Collins, the command module pilot, would remain in orbit around the moon, ensuring their safe return. Each man represented years of training, sacrifice, and determination, not only for themselves, but for the hundreds of thousands of people who had built the spacecraft, calculated the trajectories, and tested every system. On July 19th, Apollo 11 entered lunar orbit. The grey, cratered surface of the moon filled the windows of the spacecraft, silent and unchanged for billions of years. The next day, Armstrong and Aldrin climbed into the lunar module, separated from the command module, and began their descent toward the surface. Collins, orbiting above, later described how he felt a mix of pride and loneliness. watching his crewmates depart while knowing he alone would not walk on the moon. Yet he also carried the heavy duty of being their lifeline should anything go wrong. Millions watched as Neil Armstrong and Buzz Aldrin prepared to descend to the lunar surface. The world held its breath during the final minutes when alarms sounded in the lunar module. Warnings from the onboard computer nearly forced a mission. Abort and fuel ran dangerously low. At the same time, the craft was descending faster than planned, overshooting its target and heading toward a field of boulders. With only seconds of fuel left, Armstrong took manual control, guiding the Eagle over the hazardous terrain. The world followed in silence, television and radio networks cutting live to mission control in Houston, where engineers and flight directors monitored every heartbeat of data. Then, finally, Armstrong's voice came through. "Houston, Tranquility Base here. The Eagle has landed." Cheers erupted in mission control, in homes, in bars, and in city streets across the world. The gamble had succeeded. Several hours later, after preparing their suits and equipment, Armstrong opened the hatch and began his climb down the ladder. A camera attached to the module broadcast the moment live to Earth. Grainy images flickered across black and white television sets, showing a ghostly figure in a bulky suit, moving slowly in the weak lunar gravity. Then came the words that would be remembered for generations. "That's one small step for man, one giant leap for mankind." Armstrong stepped onto the lunar surface, the first human being to set foot on another world. In that instant, history was made. People in cities and villages across every continent stopped what they were doing to watch. In New York, crowds gathered in Times Square to stare at giant screens. In London, thousands listened on radios and television broadcasts. In Tokyo, children sat up past midnight, eyes wide as they watched the first steps unfold. Even in countries far from the superpower rivalry, the achievement was celebrated as something larger than politics. For the first time, humanity had crossed the boundary from Earth to another world. Buzz Aldrin soon joined Armstrong on the surface. Together, they spent about 2.5 hours exploring, collecting rock samples, and setting up experiments. They planted the American flag, but Armstrong was careful to emphasize that the landing was not just for one nation. A plaque left on the lunar module read, "We came in peace for all mankind." Though the Apollo program had been born of rivalry, in that moment it felt as if humanity itself had taken the step forward. The landing was the first truly global television event, uniting more than 500 million people in a single shared moment. Children dreamed of becoming astronauts and artists. Writers and musicians found inspiration in the images of humans walking on another world. Scientifically, the mission provided invaluable knowledge. The samples brought back helped scientists study the moon's history and its relation to Earth. The instruments left on the surface gathered data for years, recording seismic activity and reflecting lasers that allowed precise measurements of the distance between Earth and the moon. For those who had worked tirelessly on Apollo, the success was deeply personal. Engineers, technicians, and flight controllers who had labored for years felt the pride of seeing their efforts rewarded. Many spoke of tears in their eyes as they watched Armstrong's first step, knowing they had played a part, however small, in the achievement. It was proof that countless individuals working together toward a single goal could accomplish something extraordinary. The waning of the Apollo era. By the early 1970s, the energy that had carried Apollo to its peak began to fade. What had once been seen as the boldest adventure in human history was starting to feel, at least in the eyes of the public and politicians, like something that had already been done. The first landing in 1969 had transfixed billions, but by the time later missions were broadcast, many people had moved on. Television ratings for live coverage plummeted. Newspapers gave the missions less space, and the sense of urgency that had defined the race against the Soviets was no longer there. The political winds had shifted as well. When Kennedy made his promise, the Cold War was burning hot, but by the early 1970s, the balance had changed. The Soviet Union had failed to land men on the moon, and its N-1 rocket program was collapsing in secrecy and failure. The United States had already proven its point. With no rival chasing close behind, the enormous cost of Apollo became harder to justify. Vietnam had dragged on far longer than many expected, and it consumed vast sums of money as well as public attention. At home, protests against the war grew. Cities struggled with poverty and unrest. The phrase, "Why spend money on rocks while people go hungry?" was repeated in protests, newspaper editorials, and congressional hearings. NASA officials defended the value of Apollo, but the questions kept coming. The government's budget decisions reflected this mood. The entire Apollo program cost more than $25 billion in 1960s dollars, which would be well over $150 billion in today's money. NASA's share of the federal budget, which had once reached nearly 4.5% in the mid-1960s, began to fall sharply. By 1970, it was less than half of that. Congress cut funds for planned missions, cancelling Apollo 18, 19, and 20 before they could leave the drawing board. Hardware that had already been built, rockets, spacecraft, training modules, was left unused. What had once been a roaring national effort became a program winding down. Apollo 13, though remembered as a triumph of human ingenuity, also revealed just how fragile the missions were. The near loss of its crew brought home the risks of lunar exploration. Each mission was expensive, complex, and dangerous. After Apollo 11, the value of putting astronauts in such peril seemed less clear to those outside NASA. A fatal accident, many feared, could turn public opinion decisively against the space program. That fear, combined with the declining interest, added to the sense that the United States had already achieved what mattered most. Inside NASA, scientists and engineers fought to preserve momentum. They argued that the later missions were producing groundbreaking science. Apollo 15, 16, and 17 had returned with lunar rovers, allowing exploration of areas far from the landing site. Hundreds of pounds of rocks were collected, including samples that told the story of the Moon's volcanic history and its violent early years. Geologists celebrated these missions as the high point of planetary science. For them, Apollo was not a completed story, but the beginning of real exploration. Yet outside the scientific community, few people noticed. The images of astronauts riding lunar rovers could not compete with the drama of Neil Armstrong's first step. Apollo 17, launched in December 1972, became the final mission. The crew, Gene Cernan, Harrison Schmitt, and Ronald Evans, pushed the limits of lunar exploration. Cernan and Schmitt spent over 22 hours outside the lunar module across 3 days, driving the rover nearly 20 miles across the valley of Taurus Littrow. Schmitt, the only trained geologist to walk on the Moon, carefully selected samples that remain invaluable today. Cernan left the last human footprints on the lunar surface, along with words that tried to capture the significance of the moment. But back on Earth, the television networks covered only portions of the mission, and the general public paid little attention. What had once been the defining image of a generation had, within 3 years, become background noise. For many Americans, the idea of building a lasting presence on the Moon felt remote from the problems of everyday life. The spirit of the Apollo age had burned bright, but burned quickly. There were attempts to redirect the momentum. NASA proposed an Apollo applications program that would use leftover hardware for new projects, including extended stays on the Moon and even missions to Mars. Most of these plans were cancelled as budgets shrank. What remained was Skylab, a space station built from an unused Saturn V rocket stage, and later the Apollo-Soyuz test project, which symbolized a new era of cooperation with the Soviet Union. These were valuable in their own right, but they were not the bold leaps into the unknown that Apollo had represented. They marked a turn towards more cautious, sustainable goals, rather than grand adventures. The choice to end Apollo was not made lightly, but it reflected a simple truth. Nations rarely sustain such vast efforts without clear competition or threat. Apollo had been born of a desperate need to prove superiority during a dangerous time. Once that urgency faded, the costs outweighed the rewards. The result was that the most extraordinary series of voyages in human history ended abruptly, leaving a gap that has stretched for decades. The Soviet Union's collapse and its impact. By the late 1970s and into the 1980s, the Soviet Union was struggling under the weight of economic stagnation, political strain, and growing internal pressure. The state that had once shocked the world by launching Sputnik and sending Yuri Gagarin into orbit was no longer the unstoppable force it appeared to be in the early years of the space race. While the Soviets continued to achieve important milestones, such as long-duration stays aboard their Salyut space stations, the grand ambition of beating the United States to the moon had quietly faded. The Soviet moon program had always been more fragile than many realized. N-1, their massive launcher designed to carry cosmonauts to the lunar surface, suffered a string of disastrous failures. 4 test flights between 1969 and 1972 ended in explosions, with one failure ranking among the largest non-nuclear blasts in history. Unlike the United States with its Saturn V, the Soviet Union never managed to create a rocket powerful and reliable enough to send cosmonauts safely beyond Earth orbit. Behind the secrecy of the Iron Curtain, these failures were hidden from the public, but within the corridors of the Kremlin and the offices of Soviet engineers, the reality was clear. The moon was out of reach. Instead, Soviet space efforts shifted toward what they could manage more effectively: space stations. The Salyut program and later Mir became symbols of Soviet achievement, allowing cosmonauts to stay in orbit for months at a time, setting endurance records that the Americans could not match during the shuttle era. While the United States had planted flags on the moon, the Soviet Union turned its focus to learning how humans could live and work in space for extended periods. This was a different path, one born of necessity rather than choice, but it allowed the Soviets to remain leaders in an important aspect of spaceflight. As the 1980s progressed, however, the Soviet Union's economic problems deepened. The costs of maintaining a global military presence, combined with falling oil prices and inefficient industries, left fewer resources for space exploration. Programs that had once been symbols of pride became harder to justify. Plans for a next-generation shuttle, called Buran, absorbed huge sums of money, but flew only once in 1988 before being abandoned. Ambitious proposals for Mars missions and advanced lunar bases never left the drawing board. The collapse of the Soviet Union in 1991 marked a turning point not just in world politics, but in the story of space exploration. The geopolitical contest that had driven Apollo and defined the early decades of the space age was suddenly gone. The United States, now the sole superpower, no longer had a rival pushing it to prove its superiority through dramatic space achievements. Without that pressure, the urgency to return to the moon or push onto Mars evaporated. For NASA, the absence of competition meant that its goals shifted. Instead of daring missions beyond Earth orbit, the agency focused on projects that fit within tighter budgets and reflected new political realities. Cooperation replaced rivalry. The most visible example was the International Space Station, or ISS. Built not as a symbol of beating the Soviets, but as a joint effort with Russia and other international partners. The very nation that had once been seen as an existential rival became a collaborator in orbit. Russian Soyuz spacecraft, once designed to compete with Apollo, became lifelines to the space station when the shuttle was grounded after accidents. During the height of the Cold War, it would have been unthinkable for American astronauts to rely on Russian rockets to reach space. Yet after the Soviet collapse, cooperation became a practical necessity. Russia's experience with long-duration missions and its proven Soyuz capsules made it an essential partner. Meanwhile, the United States brought funding and the shuttle's heavy lift capability. Together, the two former rivals created a project that neither could have achieved alone under the conditions of the 1960s. Still, the loss of rivalry had its cost. Without the sense of competition, the drive to push boundaries weakened. The Apollo program had shown what was possible when nations poured resources into space to prove their dominance. After the Cold War ended, no such motivation remained. For many who had lived through Apollo, the post-Cold War years felt like a retreat. Decades passed without a single human traveling beyond low Earth orbit. Children who had watched the moon landings grew into adults and then into parents and grandparents without ever seeing a similar milestone achieved again. In Russia, the transition was even more painful. The Soviet space program had been a symbol of national pride, but after 1991, funding collapsed. Facilities fell into disrepair, workers went unpaid, and ambitious projects were shelved indefinitely. Engineers who had once designed rockets and spacecraft were forced to find work elsewhere, sometimes even selling their expertise abroad. Russia continued to fly missions, but often with limited resources, keeping its space program alive more through determination than through strength. And yet, in a paradoxical way, the collapse of the Soviet Union helped ensure the survival of human spaceflight. By joining forces, the United States and Russia kept crews in orbit continuously from the year 2000 onward, something neither nation could have achieved alone in those years. The International Space Station became a living laboratory, a symbol of what could happen when former enemies worked together. The International Space Station, a different kind of progress. The ISS was born from two different paths. On one side, the United States had been planning a station called Freedom, a project announced by President Reagan in the 1980s as an answer to Soviet successes with long-duration missions. On the other, Russia inherited the legacy of the Mir station, which had become the most advanced outpost in orbit during the late 1980s and early 1990s. Both nations faced challenges. America's Freedom design was expensive and politically troubled, while Russia's Mir was aging and its funding had dried up after the collapse of the Soviet Union. Instead of pursuing separate paths, the two sides merged their plans. Along with contributions from Europe, Japan, and Canada, the International Space Station began to take shape. Construction started in 1998 with the first module, Zarya, launched from Russia. Over the next decade, the ISS grew piece by piece, assembled in orbit by astronauts flying on the space shuttle and cosmonauts arriving on Soyuz capsules. Each module added new capabilities: laboratories, living quarters, solar panels, and docking ports. By the mid-2000s, it had become the largest human-made structure in orbit, stretching longer than a football field and glowing brightly as it passed overhead. The ISS was unlike anything that had come before. More than a dozen nations contributed, whether through funding, hardware, or experiments. Europe built the Columbus Laboratory, Japan built Kibo, and Canada provided the robotic arm that became essential for construction and maintenance. Crews were drawn from many countries, turning the station into a place where politics on Earth mattered less than the shared challenges of survival in orbit. Living on the ISS was a very different experience compared to the short stays of Apollo. Astronauts and cosmonauts rotated in and out, often staying for 6 months at a time, sometimes longer. They conducted scientific experiments, ranging from studying the effects of microgravity on the human body to testing how plants grow in space. They monitored Earth's climate, studied cosmic radiation, and served as test subjects for the long-term effects of spaceflight. The station became a laboratory for questions that needed answers before humanity could dream of going to Mars or building colonies beyond Earth. But while the ISS represented progress, it also showed the limits of human ambition after the Apollo era. The station orbits about 400 kilometers above Earth, a distance tiny compared to the nearly 400,000 kilometers to the Moon. For all its complexity, the ISS never strayed beyond low Earth orbit, the same region first reached by Yuri Gagarin in 1961. Decades of work, billions of dollars, and the effort of many nations kept humans in space continuously, but only within sight of Earth's surface. The reasons for this were practical. Building and maintaining the ISS was enormously expensive. At over $100 billion across decades, it consumed much of NASA's budget, leaving little room for daring ventures beyond Earth orbit. For Russia, still recovering economically in the 1990s, the partnership was a way to keep its space program alive. For Europe, Japan, and Canada, it was a chance to be part of a major space project without shouldering the cost of going it alone. The result was a station that served science, diplomacy, and human presence in space, but did not drive humanity outward. Life aboard the station was a mix of routine and challenge. Crews spent much of their time maintaining the station itself, fixing equipment, upgrading systems, and ensuring that the outpost could continue to function in the harsh environment of space. Experiments filled the remaining time, but survival always came first. Astronauts had to exercise daily to prevent their muscles and bones from weakening in microgravity. They had to carefully monitor oxygen, water, and carbon dioxide levels, knowing that even a small failure in the life support systems could be deadly. Every spacewalk, every repair, carried risk. The station was a marvel of engineering, but it was also fragile, constantly requiring attention. Despite these challenges, the ISS created a sense of continuity. After Apollo ended, there had been long gaps with no humans beyond Earth. The shuttle had carried crews into orbit, but flights were short and temporary. With the ISS, humanity achieved something new, a continuous presence in space. Since November 2000, there has always been at least one person in orbit watching over the planet. This unbroken record of human spaceflight is one of the ISS's greatest achievements. American astronauts trained in Russia, Russian cosmonauts worked alongside Europeans and Japanese in orbit, and crews from countries with little history of spaceflight had the chance to fly to the station. The ISS became a classroom for the world, where astronauts filmed experiments for schoolchildren and conducted live conversations with classrooms on Earth. It brought space down to a human level. Still, the limitations could not be ignored. As the years passed, critics pointed out that the ISS consumed vast resources without pushing exploration forward. Missions to the Moon or Mars remained only concepts, while the station circled endlessly overhead. To some, it felt like humanity was marking time, waiting for a new spark to reignite the spirit of exploration. The ISS was progress of a kind, but it was progress constrained by politics, cost, and caution. 50 years without the Moon. Half a century has passed since human beings last walked on the Moon. For those who watched Apollo 11 live, the memory is sharp and powerful. But for later generations, the moon landings have existed only in books, photographs, and old television footage. What was once the greatest adventure of humankind has slowly transformed into history, something to be studied rather than lived. For many, this created a sense of loss. The moon landings had promised a future where space was within reach, where exploration was a matter of time and willpower. Instead, people saw decades go by without a return. The Apollo missions became museum pieces, their hardware displayed behind glass. The silence marked a gap in direct human experience of another world. For over 50 years, every person who has ever lived in space has remained within the same thin shell around Earth. No one born after 1972 has known what it feels like to look up at the sky from the surface of another celestial body. This gap changed how people viewed exploration. Space travel came to mean satellites, telescopes, robotic missions, and the space station, rather than great leaps to new frontiers. The rovers on Mars, the probes to the outer planets, and the observatories peering into the universe achieved remarkable things. But they were different from seeing humans step onto alien soil. Robots could go farther, last longer, and cost less. Yet they lacked the emotional power of a single astronaut's footprint pressed into grey dust. The moon became less of a destination and more of a symbol. It was used in films, stories, and songs as an image of what humanity had once achieved and what it might achieve again someday. But for most people, it remained frozen in time. The excitement of the 1960s faded into nostalgia. There was a sense of unfinished business, The Apollo astronauts had explored only 6 small areas on the Moon. They had stayed for just a few days each time, leaving behind instruments, flags, and footprints. The surface remained largely untouched. Scientists knew that the Moon still held secrets about the early history of Earth and the solar system, yet for 50 years, those questions remained unanswered by human presence. Entire regions of the Moon had never been visited, and decades of new technology had passed without being used to expand that record. Why had a goal that once seemed so urgent been allowed to fade? Did people simply grow used to the idea, losing the wonder that had once made the impossible feel necessary? Generations grew up with the idea that humans could go to the Moon but chose not to. The knowledge that it was possible made the absence more striking. This gap is a lesson in how quickly progress can stall. The leap from the first satellite to the first moon landing had taken just 12 years, yet more than 4 times that amount of time has passed without another landing. The arc of history does not follow the straight line of constant advancement that many expect. Instead, it curves, slows, and lingers. The future imagined in the 1960s, with colonies on the Moon and humans venturing to Mars by the end of the 20th century, did not come to pass. Instead, the future became smaller, more cautious and tied to Earth orbit. The absence of moon landings has made the Apollo astronauts themselves stand out as unique figures in history. They are the only 12 people who have ever walked on another world. As time has passed, their ranks have thinned, and their experiences have become even more valuable. With every passing year, the distance between their era and the present grows wider, turning their journeys into something that feels almost legendary. 50 years without the Moon is a reflection of how human priorities shift, how politics and budgets shape destiny, and how dreams can fade even when they are within reach. It is a reminder that progress is not guaranteed, that the path of exploration is not always upward. The Moon, once touched, became distant again, not because it was out of reach, but because it was no longer pursued. China's rise as a space power. As the 2 Cold War giants slowed their pace, another power was quietly and steadily building its own path upward. By the turn of the 21st century, China had begun to emerge as the new determined player in the great story of space. China's rise in space has unfolded step by step, following a methodical plan. In the early years, China was mostly focused on launching satellites, building rockets, and gaining the basic technological foundation that the US and the Soviet Union had already mastered decades before. But unlike many countries that achieved such milestones only to stop, China kept moving forward. By the 1990s, it had begun working towards sending its own astronauts, known as taikonauts, into space. In 2003, China launched its first human spaceflight, Shenzhou 5, carrying Yang Liwei into orbit. This moment marked China as the 3rd nation in history, after the Soviet Union and the United States, to independently send a human into space. China had entered the arena of human spaceflight not as a passenger or junior partner, but on its own terms. The achievement drew attention worldwide and signaled that the long pause in space rivalry might be ending. From that point, China moved with steady purpose. Additional Shenzhou missions followed, testing more complex systems and carrying multiple taikonauts. Unlike the United States, which had grown cautious after shuttle accidents, and unlike Russia, which struggled with limited funds, China's program advanced in a deliberate and focused manner. Each mission was designed to build toward the next, each success laying the groundwork for larger ambitions. One of the key goals was building experience in long-duration spaceflight. China launched its own small space laboratories, Tiangong-1 in 2011 and Tiangong-2 in 2016. These were not full-scale stations like Mir or the ISS, but they gave China practice in docking, life support, and maintaining crews in orbit. These laboratories served as training grounds, teaching Chinese engineers and taikonauts the lessons needed for sustaining larger outposts in the future. At the same time, China looked outward, beyond Earth orbit, toward the Moon. While the United States and Russia stayed focused on near-Earth projects, China began sending robotic explorers to the lunar surface. The Chang'e program, named after a goddess of the moon in Chinese mythology, unfolded in stages. Early missions orbited the moon and mapped its surface. Later missions landed on it, something no nation had done since the 1970s. In 2013, the Chang'e 3 mission successfully delivered the rover U-2, or Jade Rabbit, marking China's first lunar landing. It was the first soft landing on the moon since the Soviet Union's Lunar 24 in 1976, breaking nearly 4 decades of silence. Chang'e 4, launched in 2019, did something no one else had attempted. It landed on the far side of the moon, a region never before touched by human technology. This showed ambition, the desire to go beyond repeating past achievements. China also advanced further by sending Chang'e 5 in 2020, which returned samples from the moon to Earth. This was the first lunar sample return since the 1970s, and it proved that China's program was not content with small steps. It was reaching for milestones that had long been left behind. Meanwhile, China pressed forward with its plans for a permanent presence in orbit. With the launch of the Tianhe core module in 2021, it began assembling its own modular space station, called Tiangong, or Heavenly Palace. Unlike the earlier small laboratories, this was designed to be a long-term outpost, with crews rotating in and out, much like the ISS. Over the next few years, additional modules were added, expanding the station's capabilities for science and habitation. By doing this, China positioned itself as the only nation other than the US and Russia to operate a large space station, at a time when the ISS was aging and approaching the end of its planned lifespan. The steady rise of China's space program contrasts with the stop-and-start nature of US exploration after Apollo. China, though starting decades later, has not slowed. Each achievement is tied to a broader roadmap, one that looks ahead not only to continued operations in Earth orbit, but also to future crewed landings on the Moon. Chinese officials have openly discussed plans to send taikonauts to the lunar surface in the 2030s, with the possibility of building a research base there. Just as with the US and the Soviet Union in the Cold War, space for China carries deep political meaning. Each mission is a demonstration of national capability, a way to show technological strength and global influence. For a country that has grown into the world's second-largest economy, space achievements serve as a symbol of rising power and modernity. While Apollo was fueled by rivalry with the Soviet Union, China's space program has been fueled by a mixture of national pride, long-term planning, and the desire to be seen as a peer to the great powers that once dominated space. The reaction worldwide has been mixed. On one hand, there is admiration for China's successes and the discipline of its approach. On the other, there is unease. For decades, the United States saw itself as the unquestioned leader in human spaceflight, with Russia as a declining partner. Now, China's rise has created the possibility of a new space race, one not about who can get there first, but about who can stay longer, go farther, and shape the future of exploration. This rivalry is not as open or direct, but it looms in the background. American plans to return to the Moon through the Artemis program are often framed with China in mind. Officials in Washington frequently speak of the need to ensure that the US does not fall behind. Meanwhile, China continues to announce new goals: future moon landings, Mars missions, and advanced technology for deep space exploration. The competition is once again shaping the timeline, pushing space exploration forward faster than it might otherwise move. The Chinese Lunar Roadmap. Chinese officials have stated that the goal is to land taikonauts by the early 2030s, and their plan appears to be aimed at building toward permanence. The early landings will likely be limited in scope, but the long-term roadmap includes the possibility of a research base, sometimes referred to as the International Lunar Research Station. While its name suggests global cooperation, the leading partners are China and Russia, with invitations extended to other countries that might wish to join. The vision for such a base is bold. It would likely begin with robotic systems establishing infrastructure, power supplies, communication relays, perhaps even 3D printed shelters built from lunar soil before humans arrive. Once in place, astronauts could rotate in and out, staying for longer periods, conducting science and testing the technologies needed for life on another world. A permanent Chinese-led outpost would be a statement of endurance and capability. China's step-by-step approach makes this vision more credible. Each mission is designed to serve as a foundation for the next, with little wasted effort. The orbiters mapped the terrain needed for landings. The landers and rovers tested surface operations. The Far Side mission proved that communications could be maintained even in difficult locations. The sample return tested ascent and docking in lunar orbit. All of these are pieces of the puzzle that must be solved before human beings can return. By completing them in sequence, China avoids the pitfalls of rushing forward too quickly. This strategy poses a direct challenge to American leadership. The United States, through its Artemis program, has declared its intention to return astronauts to the moon by the middle of this decade, with the long-term goal of building a sustainable presence at the lunar South Pole. But the program has faced delays, shifting timelines, and the political pressures that have long shaped NASA's destiny. China, meanwhile, has pressed forward with fewer disruptions, moving at its own pace, but always moving. If Artemis stumbles while China advances, the balance of leadership in space could tilt in ways not seen since the early 1960s. Both China and the United States are targeting the south pole of the moon. This region is believed to contain water ice hidden in permanently shadowed craters, a resource that could be vital for long-term habitation and fuel production. Whoever establishes a strong presence there first will not only achieve a scientific breakthrough, but also secure a symbolic foothold in what many see as the most valuable real estate on the moon. China's lunar roadmap is also supported by its broader space capabilities. The Long March rocket family has grown more powerful, and new heavy-lift designs are in development to carry the loads required for human missions to the moon. The new generation of spacecraft, such as the next-generation crewed capsule tested in 2020, is being built with deep space missions in mind. These developments show that the roadmap is being matched with the hardware needed to carry it out. For the first time in decades, the United States faces the prospect of being matched or even overtaken in human space exploration. Apollo gave America an enduring image of leadership, but the half-century without new moon landings has left room for others to rise. China's lunar roadmap suggests that the next chapter of exploration may not belong to the nation that went first, but to the nation that commits to going farther and staying longer. The impact of that shift would be felt not only in science, but in politics, culture, and the way humanity thinks about its place in the universe. The US response, Artemis and beyond. The United States could not remain absent from the moon forever. As China pressed forward, American leaders recognized that if they did not act, the image of space leadership might slip away. The answer came in the form of the Artemis program, named after the twin sister of Apollo in Greek mythology. It was framed as the beginning of a sustained return, one that would not only put astronauts back on the lunar surface, but also establish the technologies and systems needed for humanity's next steps beyond. Artemis was designed with lessons from the past in mind. It was presented not just as a single program, but as part of a broader strategy for exploration, one that could eventually stretch to Mars. The moon in this vision was not the finish line, but the testing ground. At the heart of Artemis is a return to the lunar surface. The program's first goal is to land astronauts near the moon's south pole. Unlike Apollo's equatorial landings, which were chosen largely for ease and safety, the South Pole offers both scientific promise and practical resources. If water ice can be extracted and turned into oxygen and fuel, it could support not just crews, but also future missions deeper into the solar system. To achieve this, the United States has invested in new technology. The Space Launch System, or SLS, is the most powerful rocket built since the Saturn V. It is designed to carry large payloads and the new Orion spacecraft, which will carry astronauts beyond Earth orbit for the first time in 50 years. Orion, unlike Apollo's command module, has been built with longer missions in mind, including the capacity to carry larger crews and remain functional for extended durations. The combination of SLS and Orion gives Artemis the lift and transport capability that earlier attempts lacked. One of Artemis's most striking differences from Apollo is the role of private companies. SpaceX, Blue Origin, and others are building landers and cargo systems that will deliver both astronauts and supplies to the lunar surface. The Human Landing System, which SpaceX is developing based on its Starship design, represents a new kind of partnership. Instead of NASA owning and operating all the equipment, the agency is buying services, leaving companies to innovate and compete. This approach is meant to reduce costs, increase flexibility, and ensure that lunar exploration is not solely dependent on government budgets and timelines. Another innovation is the Lunar Gateway, a small space station that will orbit the Moon. Unlike the International Space Station, which circles Earth, the Gateway will act as a staging post for missions to the lunar surface. Astronauts will dock there in Orion, transfer to landers, and then descend to the Moon. It will also serve as a hub for science and as a base for testing systems that might later be used for Mars. Though critics argue that it adds complexity, the Gateway reflects the long-term vision of Artemis, building a framework of infrastructure rather than just a series of missions. NASA has pledged that the program will land the first woman and the first person of color on the Moon. This is not just a statement of inclusion, but a reflection of how space exploration has changed since the 1960s. The Apollo astronauts were all white men, drawn from military test pilot backgrounds. Artemis aims to represent a broader slice of humanity, emphasizing that the Moon is not just for a select few, but for all. This effort also helps build public interest, reminding people that space is a shared frontier, not the domain of one group. The program is not without challenges. SLS has faced delays and cost overruns. Orion has taken longer to develop than planned. The first Artemis mission, an uncrewed flight around the Moon in 2022, was successful, but subsequent missions have slipped on the schedule. Landing astronauts by the middle of this decade remains an ambitious target, and many experts believe the timeline may stretch into the later 2020s. These delays are reminders of how complex lunar exploration remains, even with decades of experience behind humanity. NASA has outlined a series of missions that will grow in scale. First orbiting the Moon, then short surface stays, then longer expeditions with more infrastructure, and eventually a permanent base at the South Pole. If successful, the 2030s could see crews living and working on the Moon for months at a time, supported by supply chains from Earth and by the resources extracted from lunar soil. The United States has invited other nations to join through the Artemis Accords, a set of agreements outlining principles for space exploration. These accords cover ideas like transparency, peaceful use, and sharing of data. Dozens of countries have signed, making Artemis a coalition effort rather than a purely American project. This mirrors the spirit of the International Space Station. In doing so, the US hopes to rally partners, while also creating a framework that contrasts with China's proposed International Lunar Research Station. Space exploration, once a competition between two superpowers, is becoming a contest of alliances and visions. Beyond the Moon, Artemis is seen as the gateway to Mars. NASA has long spoken of sending astronauts to the Red Planet, but the technological and logistical hurdles are immense. The Moon offers a nearby proving ground to test life support systems, habitats, and propulsion technologies. If astronauts can live on the lunar surface using local resources and relying less on constant resupply from Earth, the lessons could be applied to Mars missions. Walking on another world has, for 50 years, been the stuff of memory and imagination. Artemis aims to turn it into something expected. a routine part of exploration rather than a one-time achievement. It is an attempt to take the extraordinary and make it ordinary, to transform the Moon from a destination into a place where humans can return, work, and stay. It is fragile, like all ambitious programs, and vulnerable to politics, budgets, and shifting priorities. But at its heart, it is a recognition that the Moon still matters. Why the Moon, not Mars? Mars is the planet that dominates most of our attention, the world that seems within reach, yet still mysterious. Many wonder why we should return to the Moon at all. After all, we went there half a century ago. Wouldn't it make more sense to aim directly for Mars, a planet with an atmosphere, seasons, and perhaps even the possibility of ancient life? The truth is that while Mars captures the imagination, the Moon makes sense as the next step. Its closeness to Earth, its environment, and its resources all make it the perfect training ground for the much harder journey that lies farther away. The Moon sits only about 384,000 kilometers from Earth. With today's technology, it takes just a few days to get there. Apollo astronauts made the trip in roughly 3 days, and modern spacecraft would take about the same time. Mars, on the other hand, is on average more than 200 million kilometers away. Depending on the alignment of the planets, a mission could take 6 months or longer just to arrive. That difference changes everything. If something goes wrong on the Moon, astronauts can be back home within days. If something fails on the way to Mars, there is no chance of a quick rescue. Every system has to work perfectly for months at a time, with no help from Earth. This distance also affects communication. Messages to the Moon take just over a second to travel each way. That allows for real-time conversations with mission control. On Mars, signals take anywhere from 4 to 24 minutes to cross the gap. That means there can be nearly a half-hour delay before a question gets an answer. Astronauts on Mars will need to make their own decisions without waiting for instructions. Practicing that kind of independence closer to Earth, where mistakes can still be corrected, is one reason the Moon is the safer training ground. Mars has an atmosphere, but it is thin and mostly carbon dioxide. It does not provide enough protection from radiation or enough pressure to support life without spacesuits and habitats. The Moon has no atmosphere at all, leaving its surface exposed to dangerous cosmic rays, solar storms, and temperature extremes. In both cases, survival requires building shelters and developing systems to protect human health. By working on the Moon first, astronauts can learn how to handle these problems in a place where supplies and help are only days away. Radiation is one of the greatest dangers for long-term missions. Earth's magnetic field shields us from much of the harmful energy streaming from space. The Moon and Mars do not have this protection. Learning how to shield habitats, use natural terrain like caves or lava tubes, and perhaps even develop portable protection systems is essential. Testing these ideas on the Moon will show what works and what doesn't before humans risk their lives on the long voyage to Mars. The Moon also offers the chance to practice extracting resources from another world. Water can be split into hydrogen and oxygen, creating rocket fuel and breathable air. If astronauts can learn to mine and process Moon ice, they could reduce their dependence on supplies from Earth. That same technology could later be applied on Mars, where water ice also exists. But testing it on the Moon first is far safer and more practical. Moving cargo, setting up habitats, and running equipment in low gravity presents unique challenges. The Moon's gravity is only about 1/6 of Earth's, enough to make walking and working very different from what people are used to. Mars has more gravity, about 1/3 of Earth's, but it will still feel strange and affect everything from how blood flows in the body to how machines operate. By spending time on the Moon, astronauts can adapt to a world that is not Earth. Missions to the Moon are also much cheaper than missions to Mars because they require less fuel, less equipment, and shorter travel times. Governments and companies can launch more missions, test more systems, and accept more failures without catastrophic losses. This allows progress to be made step by step, building confidence and experience. Jumping straight to Mars would mean committing enormous resources to a mission with little room for error. Failure there would not just be a setback. It could end human exploration for decades. There is also the matter of psychology. Living away from Earth for months or years at a time will test the human spirit as much as the body. Astronauts will face isolation, confinement, and the constant pressure of survival. The International Space Station has taught us much about living in orbit, but the view of Earth out the window provides comfort. The Moon, though distant, still shows Earth as a bright, recognizable presence in the sky. Mars will not offer that. To prepare crews for that level of distance, it makes sense to first test human endurance on the Moon. Many nations have expressed interest in lunar exploration, and programs like Artemis are already bringing together a coalition of partners. By the time humans are ready to attempt Mars, the groundwork for international collaboration will be stronger. Without the Moon as a shared first step, such cooperation might be harder to achieve. The Moon is not just practice, though. It is also valuable in its own right. Its geology preserves the history of the solar system in ways Earth does not. Samples from different regions could reveal secrets about the early days of the planets, the bombardment of asteroids, and even the origins of life. Exploring its craters, mountains, and volcanic plains can answer questions no less important than those we seek on Mars. In this sense, the Moon is both a scientific destination and a stepping stone. Mars will remain the long-term goal, but the Moon is the bridge that makes it possible. To ignore it would be like trying to cross an ocean without first learning how to cross a lake. From competition to collaboration. On one hand, the United States and China are both determined to show their independent strength, but on the other hand, the very nature of exploring space creates situations where cooperation might be necessary or at least beneficial. The Moon encourages this strange balance. It is too close, too visible, and too symbolic to be left to one nation. The moment one country lands astronauts there, the whole world sees it. This makes it tempting for governments to push hard for national achievements. But at the same time, the Moon is a harsh place, with no air, no protection from radiation, and no resources that can be easily accessed without new technology. Building something lasting there requires long-term work, and that is difficult for any one country to sustain alone. The combination of danger, cost, and complexity means that even competitors may find themselves drawn into some form of collaboration, whether official or unofficial. One of the clearest examples of this already exists. While the United States has banned direct cooperation with China on space projects for political reasons, both nations share data openly through international scientific bodies. Information about lunar mapping, radiation environments, and geological findings is exchanged because it benefits everyone. Scientists in China, the US, Europe, and beyond rely on shared data to understand how the Moon works as a system. These exchanges are not the same as joint missions, but they show how even in rivalry, cooperation slips in through the cracks. Knowledge does not respect national borders in quite the same way as politics does. There are also hints that in the future, larger agreements may become unavoidable. If multiple nations begin building permanent stations on the Moon, they will need to coordinate on where to land, how to avoid interfering with each other's operations, and how to share access to limited resources. There are only a few spots on the lunar South Pole that receive sunlight most of the year, making them prime real estate for future bases. If several countries rush to occupy these areas without coordination, conflict could easily arise. To prevent this, rules and frameworks will have to be developed, perhaps under the guidance of organizations like the United Nations or through treaties similar to those that govern Antarctica. Another area where collaboration might appear is in technology development. Building spacecraft, habitats, and life support systems that can last for years on the Moon is a huge challenge. Different nations are pursuing their own solutions, but once they reach a certain point, sharing technology might become practical. If one country develops an efficient way to produce oxygen from lunar soil, while another designs a reliable system for storing and using it, both might benefit from combining efforts. This could save time, reduce costs, and improve safety. Of course, national security concerns will always make governments cautious about sharing sensitive technology, but history shows that even during tense times, carefully managed exchanges can happen. Commercial companies are also adding pressure toward collaboration. Unlike the Apollo era, space exploration today involves private players who work with multiple partners across national lines. SpaceX, for instance, provides launches not only for NASA but also for international customers. European companies supply components used in American and Japanese spacecraft. If companies one day transport cargo or even people to the moon, they will almost certainly serve multiple governments. This naturally creates a network of cooperation that exists alongside the political rivalry. Companies want to maximize profits and spread their risks, and that means building bridges even where governments build walls. There is also the simple fact that disasters in space have a way of pulling nations together. If a spacecraft runs into trouble, other countries often step in to help, regardless of politics. This was true in 1975 when the Apollo-Soyuz test project saw American and Soviet spacecraft dock during a time of political tension, partly to test emergency rescue procedures. It has also been seen on the ISS, where astronauts from different countries rely on each other's equipment and training. On the Moon, where dangers are greater and rescue far more difficult, the need for backup support could push nations toward creating agreements that allow for mutual assistance. Of course, not all forms of cooperation are direct or visible. Sometimes it happens simply by learning from each other. When one nation lands a spacecraft on the Moon and demonstrates a new technique, others watch closely and adapt those lessons for their own missions. This kind of indirect cooperation accelerates progress across the board, even when governments remain rivals. In a way, the success of one mission becomes a gift to all humanity, since it proves what is possible. Looking further ahead, some imagine a time when competition gives way to a more unified approach. If humanity begins to establish larger settlements or industries on the Moon, it may become clear that cooperation is the only sustainable path. A lunar base with multiple national modules, much like the ISS, could be one outcome. Another possibility is that countries agree to divide responsibilities. One might focus on energy production, another on mining, another on transport. This would mirror the way international projects work on Earth, where different partners specialize while sharing the benefits. At the same time, it would be naive to think that competition will disappear. Nations will continue to see space as a way to show strength, secure influence, and gain access to resources. Flags will still be planted and achievements will still be celebrated as national victories. But alongside this, collaboration will grow in the shadows, sometimes quietly, sometimes openly. The two forces are not opposites so much as partners in a dance that has shaped space exploration from the very beginning. Rivalry pushes nations to act quickly, to take risks, and to innovate. Collaboration helps spread the burden, increases safety, and reduces conflict. Each depends on the other, and together they create momentum. As the world enters this new era of lunar exploration, the balance between competition and cooperation will likely decide not only who reaches the Moon first, but what we build there and whether it lasts. Artemis 1, testing the new era. When the Artemis program was first announced, many people wondered if it would really move forward or if it would end up as another ambitious plan that never left the drawing board. For decades after Apollo, proposals for returning to the Moon had been made and abandoned. Politicians promised bold missions, but funding dried up or priorities shifted. Artemis I launched in November of 2022 after several delays, each one adding to the pressure. The mission used SLS, which had been in development for years, facing cost overruns and technical setbacks. Critics doubted it would ever fly. When it finally did, the roar of its engines was a sigh of relief. Billions of dollars and years of engineering had come together, and the rocket carried with it Orion, the vessel designed to take humans into deep space once again. Artemis I carried no crew, The purpose of the mission was to test systems in conditions as close as possible to a real lunar mission without risking astronaut lives. Orion separated from the rocket and began its long journey beyond the Earth. It did not just circle the Moon as Apollo 8 had done decades earlier. Instead, it entered a distant retrograde orbit, a unique path that allowed engineers to push Orion's systems to their limits. This orbit took it farther from Earth than any spacecraft built for humans had ever traveled before, more than 430,000 kilometers away. Inside Orion were mannequins equipped with sensors standing in for astronauts. They recorded levels of radiation, vibration, and stress during the mission. The spacecraft also carried small payloads, including science experiments and CubeSats, which were released to study the Moon and deep space. Every part of the mission was designed to collect data, to reveal weaknesses, and to prove that Orion could survive the harsh environment of deep space travel. One of the most important challenges was re-entry. When a spacecraft returns from the Moon, it slams into Earth's atmosphere at speeds far greater than those coming back from low Earth orbit. The heat shield must withstand temperatures of nearly 2,800 degrees Celsius. Apollo's heat shields had proven effective decades earlier, but this was a new design and it had to be tested in real conditions. Engineers knew that if the shield failed, future astronauts would be in deadly danger. Artemis I gave them the chance to confirm it worked before any human set foot inside. The flight lasted 25 days, and during that time, Orion traveled more than 2 million kilometers. It captured stunning images of Earth and the Moon together. The spacecraft completed its orbit around the Moon, then returned to Earth, hitting the atmosphere at nearly 40,000 kilometers per hour. The heat shield glowed and burned, plasma surrounded the capsule, and then, as designed, the parachutes deployed. Orion splashed down safely in the Pacific Ocean, where recovery teams retrieved it for detailed inspection. It proved that the systems built over so many years actually worked. It silenced, at least for a while, the critics who argued that SLS and Orion were too expensive or outdated. Artemis I showed that the infrastructure for lunar missions was real, not just PowerPoint slides and press releases. The mission demonstrated that NASA had the ability to reach beyond Earth orbit again. At the same time, Artemis I revealed the challenges ahead. The mission had been delayed multiple times before launch, and the cost of developing SLS and Orion had risen into the tens of billions of dollars. Even after its success, questions remained about whether NASA could sustain the program over the long term. Each Artemis mission would require enormous resources, and history had shown that political will could fade quickly. Yet the success of Artemis I gave NASA momentum. It provided a tangible achievement that leaders could point to when arguing for continued support. The Orion spacecraft included the European Service Module, built by the European Space Agency. This provided power, propulsion, and life support systems. Its successful performance during the mission highlighted how Artemis was a partnership. Future missions would rely even more on global cooperation, and Artemis I showed that such collaboration could deliver results. Images of Earth rising over the lunar surface spread widely online, drawing comparisons to the iconic Earthrise photo from Apollo 8. These pictures served as reminders that space exploration still had the power to inspire, to make people look beyond daily concerns and consider humanity's place in the universe. Engineers pored over the data for months after Orion's return. They studied the heat shield's performance, the spacecraft's navigation systems, and the radiation levels inside the capsule. Every finding would feed into Artemis II, the first crewed mission, which is planned to carry astronauts around the Moon. The lessons of Artemis I were essential to making sure that flight would be safe. Without this uncrewed test, the risks would have been unacceptable. In that sense, Artemis I acted as a bridge, carrying the program from plans and dreams into the realm of real human missions. Artemis II and Artemis III, humans return. When Artemis I splashed down in the Pacific Ocean, attention quickly turned to what would come next. the focus shifted to Artemis II, the first time in over 50 years that astronauts would ride a spacecraft designed to travel beyond low Earth orbit. Generations had grown up watching astronauts circle Earth aboard the Space Shuttle or the International Space Station, but no human had gone farther than a few hundred kilometers from the planet since Apollo 17 in 1972. Artemis II is planned as a crewed mission that will carry 4 astronauts around the Moon. They will not land, but their journey will take them farther than any person has traveled in half a century. This mission is about proving that humans can once again survive the journey into deep space. The astronauts will test the life support systems inside Orion, practice manual controls, and confirm that the spacecraft can keep them safe for the length of a lunar voyage. The crew selected for Artemis II reflects both tradition and change. Like Apollo, the mission will be flown by highly trained astronauts with backgrounds in aviation and spaceflight. But unlike the 1960s, the team will include greater diversity, showing how space exploration has opened to people who would have been excluded in earlier decades. Their journey will be broadcast worldwide, and millions will follow their progress. After Artemis II, the real test comes with Artemis III. This mission is intended to place astronauts on the lunar surface. Unlike Apollo, Artemis III will not rely on a single vehicle. Orion will carry the astronauts into lunar orbit, but the landing itself will be carried out using a new human landing system developed with the help of commercial companies. The chosen design, led by SpaceX, is a modified version of their Starship vehicle. This means that the mission represents not just the work of NASA, but a new partnership between government and private industry. The landing itself will be a moment watched by billions. When Neil Armstrong and Buzz Aldrin stepped onto the surface in 1969, people around the world stayed awake through the night to watch. With modern technology, the Artemis landing will be broadcast in ways that allow far more people to witness it live and in high detail. The astronauts' words, the first steps, the raising of a flag, and the science they conduct will all echo across the planet. For those alive today, it will be the closest experience to reliving the spirit of Apollo, while also marking a new chapter in humanity's story. Canada, Europe, and Japan are all contributing to Artemis, providing technology and expertise. The astronauts flying on Artemis II include a Canadian crew member, a first in lunar exploration. These missions will push astronauts into deep space for the first time in decades, exposing them to higher radiation levels and the dangers of being far from immediate rescue. The technology, while tested, is still new. A failure during Artemis II or III could have serious consequences not only for the crews, but also for the future of the program. That is why every step, every system, and every maneuver must be carefully tested and rehearsed. If Artemis III succeeds in landing humans before China does, it will reinforce American influence in space. If delays or failures occur, the balance could shift. For the astronauts chosen to fly, the missions will be life-defining. They will carry the hopes of millions with them. Their journeys will be remembered, not just for what they achieve, but for what they inspire. Gateway, a space station around the Moon. The Lunar Gateway is not meant to be another international space station. It will be far smaller, at least in its early stages, with only a few modules. Whereas the ISS circles Earth only a few hundred kilometers above the surface, Gateway will be placed in a special orbit around the Moon, called a near-rectilinear halo orbit. This path will allow it to remain stable while giving access to the lunar South Pole, where astronauts are expected to land. From Gateway, crews can transfer to landers, conduct experiments, or prepare for longer missions. In Apollo, once a mission ended, there was nothing left behind to build on. Gateway changes that by providing a permanent piece of infrastructure in lunar orbit. Every new mission can connect to it, add to it, and use it as a platform. Supplies can be delivered ahead of time, systems can be tested and maintained, and astronauts will have a safe place to retreat to if something goes wrong on the surface. Europe is contributing habitation and refueling modules. Canada is supplying a robotic arm called Canadarm3, and Japan is supporting logistics and life support systems. This mirrors the model of the ISS. Living in lunar orbit will expose astronauts to radiation levels far higher than what they experience on the ISS. It will also mean greater communication delays and fewer chances for emergency rescue. Gateway becomes a testing ground for the systems needed to protect humans on long-duration missions, especially those that may eventually go to Mars. From power systems to shielding to navigation tools, everything that works on Gateway can be applied later for deeper exploration. Getting astronauts and equipment onto and off the Moon is complex. With Gateway in place, cargo ships can bring supplies directly to the station and store them until needed. Astronauts can arrive separately, reducing the need for everything to launch at once. Landers can dock, refuel, and be reused instead of being discarded after each trip. This modular approach spreads out the challenges and costs, making exploration more flexible and less dependent on one perfect launch. The small outpost in lunar orbit will not only support Artemis landings, but could also serve as a hub for robotic missions, science experiments, and even commercial activity. It turns the Moon into a base of operations instead of just a destination. There are critics, of course. Some argue that Gateway is unnecessary, that NASA could land directly on the Moon as Apollo once did without building a station first. They see it as an added layer of complexity and cost. But supporters believe that it is a vital step towards sustainability. Without infrastructure, every mission risks being a one-time achievement. With Gateway, each mission can build on the last, slowly constructing the capabilities needed to stay longer and go further. The orbit chosen for Gateway also reflects strategic thinking. The near-rectilinear halo orbit gives constant access to sunlight for solar power and regular communication with Earth. It also provides a vantage point for studying both the Moon and deep space. From this orbit, Gateway could host telescopes, instruments, and experiments that benefit science beyond just exploration. Its position makes it a flexible platform, not limited to a single task. Any crewed journey to Mars will take months. Before committing to that, NASA needs to test how systems hold up in deep space for extended periods. Gateway offers that chance. Astronauts living there for weeks or months will give valuable insight into radiation exposure, psychological stress, and the durability of spacecraft systems. It becomes a rehearsal stage for humanity's first interplanetary journeys. The design of Gateway also allows for expansion. The initial modules will provide only basic functions, power, docking ports, and small living quarters. Over time, more pieces can be added, turning it into a more capable outpost. This gradual growth mirrors the way the ISS was assembled over decades. By starting small and building over time, Gateway can adapt to new goals, technologies, and partners. Even with its small size, the Gateway represents a pivot from short-term exploration to long-term presence. For young engineers and scientists, the idea of working on a station around the Moon is no longer a dream but an opportunity that may come within their careers. The role of commercial partners. When the Apollo program was in motion, nearly every part of the mission was designed, built, and operated by NASA or companies working under strict government contracts. The approach was centralized, focused, and entirely controlled by a single vision. That model worked for Apollo, but it was also extremely costly. After the excitement of Apollo faded, budgets shrank and the United States pulled back from deep space exploration. Now, in the Artemis era, the model has shifted. Instead of NASA alone carrying the weight, private companies have become central players. This not only lowers costs, but also speeds up innovation while spreading the risk. The involvement of commercial partners has reshaped the way America thinks about space exploration, making Artemis as much a story of business as it is of science. SpaceX, Blue Origin, and several other companies now play key roles in the Artemis missions. Their involvement is not an afterthought, but built into the program from the start. NASA has chosen to buy services from these companies, rather than own every piece of hardware outright. That means companies are asked to design rockets, landers, and support systems that NASA can use. but the companies also keep rights to the technology and may use it for other markets. The idea is to create a larger space economy where moon missions are not just government projects, but stepping stones to commercial opportunity. SpaceX's Falcon 9 rockets already serve as NASA's main way to send astronauts to the ISS, but Artemis has drawn it deeper into lunar operations. NASA awarded SpaceX the contract to develop the human landing system for Artemis III, and SpaceX proposed a version of its massive Starship rocket modified to operate as a lunar lander. Unlike the Apollo lander, which was small and cramped, Starship is designed to be huge, capable of carrying many tons of cargo in addition to astronauts. If successful, it could change the way humans think about living and working on the lunar surface. The spacecraft would not only drop astronauts onto the moon, but potentially allow large-scale construction, science, and industry. Blue Origin has also been brought into the Artemis program, securing its own contract to develop a lander for later missions. Founded by Jeff Bezos, the company has long stated its goal of building a permanent human presence in space. Its lunar lander, called Blue Moon, has been in development for years. While SpaceX won the first major contract, NASA has made clear that multiple companies will be needed to ensure long-term success. Competition between SpaceX and Blue Origin mirrors the rivalry between nations. But in this case, it is meant to benefit NASA by providing multiple solutions and backup options. The two companies offer different designs, approaches, and technologies, all feeding into a program that must survive setbacks and delays. Beyond the high-profile names, there are many other commercial players. Companies like Dynetics, Lockheed Martin, Northrop Grumman, and Astrobotic are each contributing parts to Artemis. Some build support systems, cargo landers, or lunar rovers. Others focus on communications, robotics, or technologies that will make working on the moon sustainable. Even smaller startups have won contracts to deliver scientific instruments and materials to the surface as part of NASA's Commercial Lunar Payload Services program. This marks a big shift from olden times, where only a handful of giant contractors worked under direct orders from NASA. Today, dozens of companies are part of the lunar economy, creating a network of shared goals and opportunities. By bringing in commercial players, NASA hopes that new technologies developed for the moon can also be used for profit in other areas. For example, companies may learn how to mine resources on the lunar surface and later apply that to asteroid mining. They may build habitats for astronauts that could eventually serve tourists. Rockets built for Artemis may also lower costs for satellites, cargo transport, or even human travel closer to Earth. Critics argue that depending on commercial companies puts too much power in the hands of billionaires like Elon Musk and Jeff Bezos. They note that these companies have their own visions of space, which may not always align with NASA's goals. There are also risks in outsourcing critical technologies. If a company fails to deliver, the whole program could face delays. NASA has had to balance these concerns by structuring contracts carefully, requiring specific milestones and spreading work across multiple partners. The idea is not to let any one company dominate, but to encourage an ecosystem where many players can thrive. At the same time, the commercial model has already shown benefits. SpaceX's reusable rockets have lowered launch costs dramatically, something NASA struggled to achieve on its own. The company's pace of testing and innovation has also pushed the entire industry to move faster. Blue Origin, though slower, brings deep pockets and a long-term vision. Smaller firms, once ignored, now have real chances to prove their worth by delivering instruments and services to the moon. Together they form a system that looks more like a living economy than a government project. This could prove crucial if humanity hopes to stay on the moon for decades rather than years. The partnership between NASA and commercial companies also sets the stage for how humans might go beyond the moon. Mars, asteroids, and even deeper space exploration will likely require the same model. No single government can afford the entire cost of building spacecraft, habitats, and transport systems at that scale. But if private companies can find profit in the process, the effort becomes shared. The involvement of commercial partners changes the tone of exploration itself. During Apollo, astronauts stood on the Moon as symbols of national pride. Now, future astronauts may stand there not only as representatives of their country, but also as part of a network that includes private companies, international partners, and future settlers. The Moon becomes not just a flag and footprints destination, but a marketplace, a workplace, and a test bed. The rise of business in space suggests that humanity's expansion into the cosmos will not follow the same path as the Cold War, but will be shaped by the same forces that shape life on Earth: competition, innovation, and the search for opportunity. Building a lunar base. The idea of building a base on the Moon has long fascinated scientists, engineers, and dreamers. A permanent outpost would mean people living and working on the lunar surface for weeks, months, or even years at a time. Such a goal is not simple. The Moon is a hostile place with no air, extreme temperatures, constant radiation, and dust that clings to everything. To survive there, every piece of technology has to be designed with care. A lunar base would not be like building a camp on Earth. It would be more like creating a small spacecraft on the ground, one that can protect its crew from an environment that does not forgive mistakes. The first challenge is habitats. On Earth, our atmosphere shields us from radiation, balances temperatures, and provides air to breathe. The Moon has none of these protections. At night, the surface drops to freezing levels far below what life can tolerate, and during the day, it can climb to scorching heat. A base must be sealed, insulated, and carefully controlled. Engineers imagine inflatable habitats that can be shipped in compact form and then expanded once on the Moon, or rigid modules similar to those on the International Space Station. These habitats would need thick walls or protective coverings to shield against radiation. One idea is to cover them with lunar soil, using the Moon itself as armor against the Sun's rays and cosmic particles. Life support is another requirement. Air must be constantly recycled, water must be purified, and waste must be managed. On the ISS, astronauts rely on complex systems that reuse water and scrub carbon dioxide from the air. On the Moon, similar systems would be needed, but they must be even more reliable since resupply from Earth would be limited. Every drop of water and every breath of oxygen would be precious. Engineers are already testing ways to use lunar resources, such as extracting oxygen from the soil or melting ice found in shadowed craters. If successful, this would reduce the need to haul everything from Earth, making a base more practical. Power is equally critical. Without energy, there can be no light, no heating, no recycling, and no communication. Solar panels are the most likely choice, especially in regions near the lunar South Pole. Some peaks in this area receive almost constant sunlight, offering a steady source of energy. Panels could be placed there and linked to the base, providing electricity year-round. In other areas, however, the long lunar night, 2 weeks of darkness, would make solar power unreliable. For those regions, engineers consider nuclear systems, such as small reactors, that could provide continuous energy regardless of sunlight. Having a dependable power supply is the foundation of survival. Beyond Earth's protective magnetic field, astronauts are exposed to high-energy particles from the Sun and from deep space. Prolonged exposure can cause serious health problems, from radiation sickness to cancer. A lunar base must therefore provide shielding. Covering habitats with thick layers of lunar soil is one option. Another is building the base partly underground, using natural caves or lava tubes formed by ancient volcanic activity. These tunnels could offer natural protection, turning them into ready-made shelters with far less construction needed on the surface. Dust may sound harmless, but lunar dust is a serious problem. The fine grains cling to clothing, equipment, and machinery. Apollo astronauts reported that it scratched visors, clogged joints, and even irritated their lungs when it got inside the lander. For a permanent base, dust control would be critical. Airlocks might need built-in cleaning systems to brush off suits before astronauts enter. Equipment would need to be designed with seals that resist clogging, Without careful planning, dust could damage systems and endanger lives. Supplies, equipment and people must be moved from orbit to the surface and back again. Landers would need to carry heavy loads safely and reliably. Once on the ground, rovers would help carry cargo, move solar panels, and transport astronauts across the rugged terrain. Over time, a network of vehicles would become essential, turning the base into something more like a settlement. Construction itself is a challenge. On Earth, we rely on heavy machinery and constant resupply of building materials. On the Moon, everything must either be brought from Earth or made from local resources. This is where the idea of in situ resource use becomes vital. Lunar soil, known as regolith, could be turned into bricks or concrete-like materials. 3D printing technology may allow habitats, landing pads and roads to be built directly from lunar dust. Using what the Moon already provides reduces costs and increases independence. Communication with Earth is also essential. Relay satellites around the Moon or the gateway station in lunar orbit will ensure constant communication. A base cannot survive without a link to mission control, scientists and engineers on Earth. Life on the Moon would be confined, dangerous, and far from the comforts of Earth. Astronauts would spend weeks or months in small habitats with limited contact outside their crew. The isolation could be difficult, and routines would be necessary to maintain mental health. Windows, greenhouses, or even virtual reality systems might be used to give a sense of connection to Earth. Growing plants could provide food and also comfort, making the habitat feel less like a sealed can in a hostile desert. The cost of such a project will be enormous. Building a lunar base requires not just new technology, but also political will and long-term commitment. A base would demand steady funding across decades, something only possible if the public and government see lasting value. That value might come from science, from national pride, or from the hope that the Moon could one day support industry and further exploration. A lunar base would also have to adapt over time. The first outpost might be no larger than a couple of small modules linked together. Astronauts would stay for short periods, testing systems and learning how to manage the environment. Later, more modules would be added, solar arrays expanded and rovers introduced. Eventually, greenhouses, mining equipment and laboratories could turn the base into a true settlement. The growth would be step by step, just as it was with the ISS. Living on the Moon. Life on the Moon is not like life anywhere on Earth. Every aspect of daily survival is challenged by an environment that is hostile to human bodies and machines. Radiation does not only threaten immediate health. Long-term exposure can cause cancer, damage to the nervous system, and other illnesses that may take years to show. This makes planning especially difficult, because Artemis is not just about sending astronauts for a few days. The vision is for extended missions, perhaps leading to permanent bases. Every hour of radiation exposure adds to the risk. Because of this, mission planners will have to carefully monitor solar activity and provide safe shelters where astronauts can retreat if a storm strikes suddenly. Then there is the problem of temperature. The Moon's day and night cycle is very different from Earth's. One day on the Moon lasts about 29.5 Earth days, meaning 2 weeks of sunlight followed by 2 weeks of darkness. During the day, temperatures can rise to more than 120 degrees Celsius. At night, they can plunge to minus 170 degrees. No natural environment on Earth swings so wildly. Habitats will need advanced insulation and heating systems to keep conditions livable. Power sources must work continuously, even during the long lunar night. Batteries, fuel cells, or even nuclear reactors may be required to keep bases running when the sun disappears for 2 weeks. A spacesuit that protects against extreme heat must also guard against bitter cold, all while being flexible enough for astronauts to move and work. The Apollo suits handled short moonwalks, but they would not last through the repeated exposure required for long-term stays. Newer suits are being designed to regulate temperature better, withstand damage, and allow astronauts to bend and move more freely. The suit is, in many ways, a personal spaceship, a life support system carried on the body. If it fails, survival time is measured in seconds. Perhaps the most underestimated challenge is lunar dust. The surface of the moon is covered in a fine, sharp powder of crushed rock created by billions of years of meteorite impacts. Unlike Earth dust, which is often rounded by weather and erosion, lunar dust has jagged edges and clings to everything. Apollo astronauts found it stuck to their suits and equipment. It caused irritation to their skin, eyes, and lungs. For long-term missions, the effects could be serious. Dust can also grind down machinery, clog filters, and reduce the efficiency of solar panels. Preventing it from entering habitats is a major focus for Artemis engineers. Some are experimenting with fabrics that repel dust using electric charges. The daily rhythm of living on the moon will also be unlike anything on Earth. With no atmosphere to scatter sunlight, the sky is always black, even during the day. The horizon is close, and the lack of familiar landmarks may make orientation difficult. Sleep cycles will need careful management since the natural day-night cycle is so long. Artificial lighting and schedules may help astronauts maintain a sense of time, but the psychological effect of such an alien environment should not be underestimated. Isolation and confinement are already challenges on the ISS, but the moon will add the weight of distance. Knowing that Earth is days of travel away will likely affect the mental health of crews. Food and water are another constant concern. Everything needed for survival must either be brought from Earth or produced locally. Transporting supplies across 400,000 kilometers of space is costly and limited, so researchers are studying how to grow plants in lunar conditions. Experiments on the ISS have shown that lettuce, wheat, and other crops can grow in microgravity. On the moon, gravity is weaker than Earth's, but still present, which may make farming easier than in orbit. However, plants will need protection from radiation and temperature extremes, meaning they must be grown inside special greenhouses or modules. Water recycling will also be critical. Every drop used for drinking, cooking, or cleaning must be reclaimed and reused as much as possible. Even with recycling, outside sources of water will be needed. The ability to live off the land will determine whether long-term bases are possible. Without it, every resource would need to come from Earth, making permanent settlement nearly impossible. Work on the moon will also be physically demanding. Moving in 1/6 gravity may look fun, as Apollo astronauts demonstrated with their long hops, but it places stress on muscles and bones in unusual ways. Staying healthy will require regular exercise, just as it does for astronauts on the ISS, where hours of daily workouts are part of the routine. Equipment for exercise will need to be compact yet effective, able to fit inside small habitats. Over months or years, even slight imbalances in muscle use could lead to injuries or loss of strength. Beyond the physical, there is the question of how astronauts will cope with the feeling of being on another world. The vast emptiness outside the habitat, the constant reminder of danger, and the knowledge that home is far away. Support from Earth will help, but real-time conversation is not possible once missions go beyond the moon. Even on the moon, communication delays, though short, may affect decision-making and personal connection. Designing social structures, leisure activities, and mental health support systems will be as important as building habitats and suits. Living on the moon is about creating a way of life that balances technology, biology, and psychology. Each day will involve careful routines, from checking air systems and power levels to keeping track of personal health and managing limited resources. The challenge is immense, but it is also what makes the Artemis program different from Apollo. Every solution developed for these problems will bring humanity one step closer to becoming residents in space. Using local resources. Rockets are powerful, but they are also limited. The more weight they carry, the more fuel they need, and the more expensive each mission becomes. For short trips, this was manageable, but for long-term stays or permanent bases, it is impossible. That is why Artemis and other modern lunar plans focus on using local resources. The moon may look barren, but its surface hides valuable materials. Over the last 2 decades, missions like NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 have confirmed evidence of frozen water trapped in craters at the Moon's poles. These craters never see sunlight, making them some of the coldest places in the solar system. Temperatures there are so low that ice can remain stable for billions of years. If this ice can be mined, it could change everything. Water is essential for drinking and growing food, but it is also a source of rocket fuel. A base that can refuel rockets from local ice would no longer depend on Earth for every mission. This is why many experts believe the first permanent lunar base will be built near one of the poles. Extracting that ice will not be simple. It is mixed with soil and rock, frozen in hard layers beneath the surface. Machines will need to dig, drill, or heat the ground to release it. Once collected, the ice must be purified and stored. Engineers are studying different ways to do this. Some propose using robots that scoop up regolith and place it into ovens, where heat separates the water vapor, which is then condensed back into liquid. Others imagine giant mirrors reflecting sunlight into craters to slowly warm the ground and release the ice. Whatever the method, it must be reliable, since a constant supply of water will be the foundation of life on the Moon. The lunar soil, or regolith, is filled with oxygen bound tightly in minerals like silicates. Although the Moon has no air to breathe, its rocks are rich with the element that makes up nearly half of their weight. Scientists are experimenting with techniques to extract this oxygen. One method is electrolysis, where regolith is melted and an electric current pulls the oxygen out, leaving metals behind. Another idea is to use hydrogen gas to react with the minerals, releasing oxygen in the process. If perfected, this could provide breathable air for habitats and fuel for rockets. Having a local source of oxygen would reduce one of the heaviest and most expensive supplies that otherwise must be launched from Earth. The leftover metals from oxygen extraction will not go to waste. Lunar soil contains aluminum, iron, titanium, and other useful materials. On Earth, these are used to build everything from cars to skyscrapers. On the Moon, they could be turned into parts for habitats, tools, or even vehicles. 3D printing technology makes this more practical. Instead of transporting bulky spare parts from Earth, a base could use regolith as raw material to print new items on demand. Some experiments on Earth have already shown that lunar soil simulants can be melted with lasers into solid blocks or shaped into simple structures. Over time, this could expand into printing entire walls, roads, or landing pads, all made from local rock. Solar power is abundant on the Moon's surface during the long 2-week daytime, and some regions are especially valuable because they receive near-constant sunlight. These peaks of eternal light could host solar farms, providing steady power almost year-round. For areas that fall into darkness, energy could come from fuel made with lunar resources, such as hydrogen from ice. The key is to create a system where power is always available, regardless of the long lunar nights or unpredictable demands of exploration. Fuel made from lunar water could transform not only Moon missions, but also space travel beyond. Rockets launched from Earth must fight against Earth's gravity, which takes a huge amount of energy. If spacecraft could instead refuel on the Moon, where gravity is weaker, it would open the door to easier missions to Mars or the outer planets. In this way, the Moon could become a gas station in space, a supply hub for journeys deeper into the solar system. Some visionaries even imagine a future economy where lunar fuel is sold to private companies or international partners, turning the Moon into the first outpost of a space-based industry. Even basic survival items like building materials may come from the Moon itself. The fine dust of the regolith could be mixed with binders to make bricks. Heated and compressed, it could form strong blocks for shelters. Shielding habitats with thick layers of regolith could protect astronauts from radiation and temperature extremes without the need to haul heavy shielding from Earth. Lava tubes, natural tunnels formed by ancient volcanic activity, could also serve as ready-made shelters. These underground spaces, found by orbiting spacecraft, are naturally protected from radiation and micrometeorites. If connected with local resource extraction, they might become the first true lunar homes. Food is harder to produce locally, but even here, resources could help. The moon's soil contains some of the nutrients needed for plants, though it lacks organic material. Scientists are testing how to grow crops in regolith simulants, often mixing them with compost or bacteria to enrich the mix. With water and artificial light, plants could eventually be grown in greenhouses built on the moon. Recycling waste into fertilizer would close the loop, reducing the need to import food. While this may take years to perfect, it is part of the long-term vision of making lunar bases more independent. Mining and processing resources will not be without risks. Machines will have to operate in harsh conditions, where dust can jam gears and extreme temperatures can break delicate parts. Repairs may be difficult if equipment fails far from the base. For this reason, robotic systems will likely be tested first, with humans overseeing them from nearby habitats or even from Earth. Over time, as confidence grows, more complex systems will be built. The transition from reliance on Earth to reliance on the Moon will be slow, but every step will add resilience to future missions. If astronauts can drink water pulled from lunar ice, breathe oxygen drawn from lunar soil, and build shelters from lunar rock, then the Moon becomes a place where humans can live. Every solution developed there will also apply to Mars and beyond. By learning to live off its resources, humanity will gain the skills needed to expand farther. The promise of lunar ice. For most of history, people looked up at the Moon and assumed it was bone dry. The grey plains and craters seemed to tell a story of a place without water, without air, and without the things that make life possible. Apollo astronauts confirmed that impression when they brought back rocks that showed no sign of moisture. For decades, the Moon was seen as lifeless and empty, a desert in space. But in recent years, that picture has changed. Because the Moon's axis is only slightly tilted, the polar regions have places where the sun never rises above the horizon. These cold traps remain in darkness for billions of years. Temperatures there can plunge to nearly minus 250 degrees Celsius, colder than Pluto. At such extremes, any water that reaches these regions, delivered by comets, asteroids, or even ancient volcanic eruptions, can remain frozen and stable. That is why scientists believe these craters may hold millions of tons of ice, locked away in soil and rock. Finding this ice was not simple. The first hints came in the 1990s, when NASA's Clementine mission bounced radar signals off the Moon and detected reflections that suggested ice might be present. Later, the Lunar Prospector mission confirmed unusual hydrogen signatures at the poles, another clue pointing to frozen water. In 2009, NASA's L-Cross mission sent a rocket stage crashing into a crater near the South Pole. Instruments aboard a trailing spacecraft studied the plume of debris kicked up by the impact and found unmistakable signs of water vapor and ice particles. Since then, other spacecraft, including India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter, have mapped the distribution of hydrogen and measured surface temperatures. Together, their results leave little doubt. The value of that ice cannot be overstated. This is why some experts call lunar ice the oil of space. Just as oil fueled the industrial age on Earth, lunar water could fuel the space age. A tank of propellant made from moon ice could send spacecraft to Mars, asteroids, or beyond. The Moon could become not just a destination, but a hub, a refueling station for missions deeper into the cosmos. The presence of ice makes the Moon a strategic prize, not only for science, but also for national power and commercial opportunity. This is one of the reasons why the renewed interest in lunar exploration has become so intense. Extracting the ice, however, will not be easy. Unlike glaciers on Earth, the lunar ice is not found in clean, thick sheets. Instead, it is mixed with dust and rock, sometimes just tiny grains of ice embedded in the soil. The extreme cold of the shadowed craters can destroy electronics and freeze machinery solid. Any mining effort will require creative engineering, reliable robots, and possibly human oversight from nearby bases. Once extracted, Storing and transporting the ice is another challenge. Water can easily sublimate, turning directly from solid to vapor if exposed to sunlight in the vacuum of space. Special containers will be needed to keep it stable. Processing plants will need to run continuously to supply a steady flow of water and fuel for crews. Unlike a short Apollo mission, a long-term base will rely on this resource for survival, so the systems must be robust and dependable. The scientific value of lunar ice is also enormous. The ice may contain records of ancient comet impacts, solar wind particles, and even the chemistry of early water delivery to Earth. Some scientists compare these polar craters to natural time capsules. Just as Antarctic ice cores reveal Earth's climate history, lunar ice might tell the story of how water moved through the solar system over billions of years. This makes the resource not only practical, but also a treasure for science. If astronauts can drink water, they mine themselves, breathe air pulled from the lunar soil, and launch rockets powered by lunar hydrogen, they are no longer visitors, but settlers. The presence of ice makes that dream real in a way that nothing else could. The poles of the moon, once ignored, have now become some of the most valuable real estate in space. Helium-3 and energy dreams. There is another material on the moon that has captured imaginations for decades: helium-3. Unlike ice, which can be used directly for survival and fuel, helium-3 is tied to a much bigger dream, the idea of limitless clean energy. This rare form of helium is almost non-existent on Earth, but the moon may hold large amounts of it in its soil. For those who believe in its potential, helium-3 could power the future, turning the moon into a source of energy for the entire planet. Helium-3 is an isotope of helium, meaning it is a slightly different version of the same element. Normal helium, the kind used to fill balloons, has 2 protons and 2 neutrons in its nucleus. Helium-3 has 2 protons, but only 1 neutron. This difference makes it valuable for nuclear fusion, the process that powers the sun and stars. Unlike today's nuclear power, which splits atoms apart in fission, fusion combines them. Fusion promises to release huge amounts of energy without the same radioactive waste or meltdown risks that fission has. The catch is that fusion is very hard to achieve on Earth. Current experiments in fusion usually use isotopes of hydrogen, like deuterium and tritium. These fuels can produce energy, but they also create high-energy neutrons that damage reactors and produce radioactive byproducts. Helium-3, by contrast, could allow for what scientists call aneutronic fusion. When fused with deuterium, helium-3 produces charged particles instead of neutrons. Those particles can be converted directly into electricity without the same level of radiation. In theory, this would make a helium-3 fusion reactor cleaner, safer, and more efficient than any energy system we have today. That is why helium-3 is often described as the perfect fuel. The problem is that helium-3 is extremely rare on Earth. Our atmosphere blocks most of the solar wind, which is where helium-3 comes from. Over billions of years, the solar wind has deposited tiny amounts of helium-3 into the moon's surface, since it has no thick atmosphere or magnetic field to shield it. Scientists estimate that millions of tons of helium-3 may be trapped in the lunar soil, especially in the fine dust known as regolith. By heating this soil to high temperatures, helium-3 could be released and collected. On paper, the numbers are astonishing. Some studies suggest that just a few dozen tons of helium-3 could supply all of Earth's electricity for a year. That has led to bold visions of mining the moon and shipping helium-3 back to power fusion plants on Earth. These visions are not new. As early as the 1980s, researchers and science writers began to talk about the moon as an energy source. Since then, the idea has often appeared in documentaries, speeches, and proposals. Countries like China and India have even mentioned helium-3 in their long-term space plans. The idea appeals because it offers a way to connect space exploration directly to life on Earth. Instead of exploration for its own sake or for prestige, mining helium-3 could solve one of humanity's greatest problems: the need for clean, abundant energy. But there are challenges, big ones. The first is technology. While helium-3 sounds like the perfect fuel, no working helium-3 fusion reactor exists today. In fact, even the more ordinary forms of fusion, using deuterium and tritium, have not yet been mastered for commercial use. Laboratories like ITER in France and other projects around the world are still struggling to achieve sustained net positive fusion, where the energy produced is greater than the energy put in. If helium-3 reactors are ever built, they will require advances in physics and engineering that we may still be decades away from achieving. Mining helium-3 would be meaningless unless we have the reactors to use it. The second challenge is mining itself. Helium-3 is not found in large pure deposits. It is spread thinly through the Moon's surface at concentrations of only a few parts per billion. That means huge amounts of soil would need to be processed to collect useful amounts. To put it in perspective, harvesting 1 ton of helium-3 might require digging up hundreds of millions of tons of lunar regolith. Machines would need to scoop, transport and heat the soil to over 600 degrees Celsius to release the trapped gases. All of this would have to happen in a place with no air, extreme temperatures and dust. The scale of the operation would be enormous, far beyond anything humanity has ever done in space. Even if helium-3 were extracted, it would have to be shipped back to Earth in large quantities. Rockets capable of carrying such payloads would need to operate regularly and cheaply, which is not the case today. Every kilogram launched from the Moon would require careful planning and energy. The economics of such an operation are not clear. Would the cost of mining, processing and shipping helium-3 outweigh the value of the electricity it could provide? Until both fusion reactors and lunar mining technologies are demonstrated, the answer remains uncertain. Despite these challenges, the dream of helium-3 has not disappeared. For some scientists, it represents the ultimate long-term goal of lunar exploration. For policymakers and engineers, it is a symbol of what might be possible if humanity learns to use space resources. Even if helium-3 never becomes a practical energy source, the idea itself has fueled interest in space exploration and inspired generations of thinkers. The nations that control access to helium-3, if it ever becomes valuable, could gain enormous influence. This possibility is sometimes raised in discussions about why countries like China, the United States, and Russia are focusing on the Moon. Even if the true value of helium-3 is unproven, no one wants to be left behind if it turns out to be the key to future energy. Just as oil shaped world politics in the 20th century, some imagine helium-3 shaping the 21st or 22nd. The Moon as a launchpad to Mars. Lifting a heavy spacecraft filled with fuel, supplies and shielding out of Earth's deep gravity well requires enormous power. Rockets leaving our planet must fight against strong atmospheric drag and high escape velocity, which makes every launch costly and limited in scale. The Moon offers a very different environment. Rockets launched from the Moon would need far less energy to reach interplanetary space. The idea is not to move everything to the Moon immediately, but to use it as a stepping stone. Imagine building a supply chain in space where resources mined from the lunar surface are turned into fuel or building materials. Cargo could be prepared and launched from the Moon more efficiently than from Earth. In this model, Earth remains the hub for advanced equipment, crew, and mission control, but the Moon becomes the workshop and fueling station. A spacecraft bound for Mars could be assembled in lunar orbit or at a lunar base, topped off with propellant made from lunar water ice and then sent on its way without needing to carry all that mass from Earth. This strategy also reduces risks. Rockets launching directly from Earth to Mars must carry everything from start to finish, leaving no room for error. If something goes wrong, there is no place to restock or repair. The Moon could provide that margin of safety. A spacecraft could be tested in lunar orbit, with astronauts able to return home more easily if problems occur. Missions could stage at a lunar depot, ensuring everything works before committing to the long, dangerous journey across interplanetary space. Some have suggested building giant electromagnetic launchers, sometimes called mass drivers, on the Moon's surface. Instead of using chemical rockets, these systems could hurl cargo into space at high speeds, where it could be caught by spacecraft or depots in lunar orbit. This would allow heavy supplies, such as fuel, raw materials, or even pre-built components, to be shipped upward without wasting large amounts of rocket fuel. While still highly experimental, such technology fits neatly into the long-term vision of the Moon as a staging ground. A Moon-based launch pad could lower the cost of interplanetary travel dramatically. Instead of every Mars mission being a rare, billion-dollar gamble, it could become part of a regular transport system. Just as Earth's oceans were once barriers until ports and trade routes were established, the solar system could open once we have a base at the Moon. Ships leaving the Moon for Mars might someday be as routine as ships leaving harbors for distant continents. If humanity proves that lunar infrastructure works, the same methods could support missions to asteroids, to the outer planets, and even to the moons of Jupiter or Saturn. For many scientists, engineers, and dreamers, this is the real reason to go back to the Moon. It is about turning the Moon into the first true spaceport. Europe's lunar ambitions. When most people think about space exploration, they picture NASA, or perhaps the rockets built by private American companies. But Europe has been a quiet yet steady force in shaping what comes next. The European Space Agency, or ESA, has been part of nearly every major international effort in space. Its scientists and engineers helped build the ISS, and they have led famous missions like Rosetta, which landed a probe on a comet, and Mars Express, which continues to study the red planet. Now, as the world turns its attention back to the Moon, Europe is not staying on the sidelines. Instead, it has made the lunar frontier a central goal, working hand in hand with NASA and other partners to ensure that this return is built on cooperation and shared science. ESA's role in the Artemis program is most visible in the Orion spacecraft. While Orion looks like an American spacecraft on the outside, its heart contains critical systems from Europe. The European Service Module, designed and built by ESA, provides the spacecraft with power, propulsion, water, and oxygen. Without it, Orion could not function. This arrangement is historic because it marks the first time NASA has relied on a partner to supply such a vital part of a human spacecraft. By contributing to Orion, ESA secures a seat for European astronauts on future Artemis missions. This means that when humans walk on the Moon again, it may not only be Americans. A European flag could stand alongside the Stars and Stripes. For ESA's member nations, which range from giants like Germany and France to smaller countries such as Luxembourg and Estonia, this is a powerful symbol of what cooperation can achieve. Beyond Artemis, Europe has its own concepts for the Moon. One of the most ambitious is the idea of a Moon Village. This vision, promoted by ESA leaders, imagines a community of astronauts, scientists, engineers, and even commercial partners working side by side on the lunar surface. The Moon Village is not about competition, but about creating an open platform where different countries and companies can contribute. Some might build habitats, others might mine resources, while others could focus on science or even tourism. Science remains at the heart of ESA's ambitions. European researchers are deeply interested in studying the Moon's geology, searching for water at the poles, and using the lunar surface as a base for astronomy. The far side of the Moon, shielded from Earth's radio noise, is a perfect place to build radio telescopes that could listen to signals from the early universe. Such projects are difficult and costly, but with multiple partners involved, they become possible. European companies are also preparing to play a bigger role. Firms in Germany, Italy, and the United Kingdom are developing robotic landers, cargo systems, and technologies for resource extraction. For example, there are plans to test how regolith can be processed to extract oxygen or metals. These experiments could one day supply astronauts with air to breathe and materials for construction. Another part of Europe's strategy is its focus on sustainability. ESA has spoken often about avoiding the mistakes of Apollo, which left behind large amounts of waste and abandoned equipment. Europe is pushing for cleaner, more efficient technologies that reduce environmental impact, both on Earth and on the Moon. This includes reusability, recycling of resources, and international rules for how to handle lunar exploration responsibly. While these ideas may sound abstract, they will matter greatly as more countries and private companies set their sights on the Moon. Without shared guidelines, the lunar surface could become crowded and chaotic. Europe hopes to lead in setting standards for responsible exploration. Europe itself is made up of more than 20 member states, each contributing funds, expertise, and ideas. No single European country could afford the scale of lunar exploration on its own, but together they form one of the world's largest space programs. This same spirit extends outward. ESA partners not only with NASA, but also with agencies in Japan, Canada, and beyond. In the Artemis program, for example, ESA is providing parts of the Gateway space station that will orbit the Moon, including a habitat module for astronauts. Once again, Europe is ensuring that it is woven into the very fabric of this new lunar network. Programs across ESA's member states are linking lunar exploration to education, encouraging young people to pursue careers in science, engineering, and technology. The story of Europe helping to send astronauts to the Moon is used to show that space is not just for distant superpowers, but for all who choose to contribute. In classrooms from Madrid to Warsaw, children are learning that they too may one day play a role in exploring other worlds. By committing to Artemis and to lunar exploration, Europe strengthens its ties with the United States and other allies. In an age when space is becoming more contested, with new players like China pushing forward aggressively, this unity matters. ESA's involvement ensures that the lunar frontier remains a place of collaboration rather than conflict. At the same time, it gives Europe a voice in shaping the rules of the game, rules about resource use, safety, and long-term strategy. Russia's shifting plans. After the Soviet Union collapsed in 1991, the Russian space program entered a difficult era. Funding dried up, and many skilled engineers left for other industries or even other countries. To keep itself alive, Russia leaned heavily on cooperation. They joined with NASA and other partners to build and operate the ISS. For years, Russian Soyuz spacecraft were the only way for astronauts to reach orbit after the US retired the space shuttle in 2011. This gave Russia a central role in human spaceflight, even if their ambitions beyond Earth orbit had stalled. When it comes to the Moon, Russia's plans have been more talk than action. Various roadmaps have been announced over the years. Some called for a new series of lunar robotic missions meant to update the achievements of the 1960s and 1970s. Others suggested crewed flights to lunar orbit, or even the building of a Russian lunar base by the 2030s. Yet again and again, these plans have slipped. Funding shortages, technical challenges, and shifting political priorities have delayed or cancelled many of the projects. In 2023, Russia attempted to revive its lunar exploration with the Lunar 25 mission, the first Russian spacecraft to head for the Moon in nearly half a century. It was meant to land near the South Pole. Success would have shown that Russia could still be a serious player in lunar exploration. Instead, the lander crashed, a painful reminder of how difficult such missions are and how far Russia had fallen behind. The failure underscored the gap between Russia's ambitions and its actual capabilities. At the same time, the geopolitical landscape has further complicated Russia's role. Tensions with the West, especially after conflicts on Earth, have limited cooperation. While Russia remains a key partner on the ISS, its long-term participation is uncertain. Moscow has spoken about building its own space station once the ISS ends, though whether they have the resources to do so is unclear. Similarly, they have expressed interest in lunar partnerships with China, including plans for a joint lunar base. This alignment makes sense. China has the funding and momentum, while Russia has decades of experience in spaceflight. But such a partnership is still mostly on paper. Russia's shifting plans also reflect the difficult balance between prestige and practicality. On one hand, the moon is seen as a symbol of national pride. Returning there would show the world that Russia is still a space power, not just a country resting on old achievements. On the other hand, spaceflight is expensive, and Russia's economy has other pressing needs. Leaders in Moscow must constantly decide whether to pour money into rockets and landers or focus on issues closer to home. This has led to a pattern of big announcements followed by long delays. Despite the setbacks, Russia still has strengths. Their launch vehicles remain reliable workhorses, even if newer rockets have faced delays. Their experience with long-duration missions gives them a unique perspective on human health in space. Their engineers understand how to build tough, practical spacecraft. If Russia can stabilize its funding and focus, it could still play a role in lunar exploration. But the competition has changed. The United States, China, and even smaller players like India are moving quickly. In this new race, hesitation can mean falling behind permanently. For now, Russia's lunar roadmap remains cloudy. More robotic missions are officially planned, building toward a presence at the moon's south pole. There are still official statements about sending cosmonauts there eventually. Yet without consistent progress, these remain distant promises. The contrast with China is striking. While Beijing steadily ticks off milestones, Russia often struggles to get a single spacecraft off the ground. This does not erase Russia's proud history in space, but it does raise questions about its future. Japan and India on the lunar stage. Japan and India have emerged as two of the most interesting players in the new era of lunar exploration. While they do not have the vast budgets of the United States or China, both nations have steadily built impressive space programs that are beginning to make their mark beyond Earth. Japan's interest in the moon goes back decades. Through its space agency, now called JAXA, Japan has launched several important robotic missions. In 1990, Japan became the third country to send a spacecraft to orbit the moon with the Haiten probe. It was a modest mission, but it demonstrated that Japan had the technical ability to reach another world. In 2007, Japan made a much larger leap with the Kaguya mission, also known as Selene. Kaguya orbited the moon and studied its surface and gravity field in great detail, sending back stunning high-definition images that captured the imagination of people around the world. It was considered one of the most successful lunar missions of its time, and showed that Japan could compete with the best in planetary science. Japan has not limited itself to science alone. It is deeply involved in international partnerships, particularly with NASA. Japan plans to supply key modules and even support logistics, helping astronauts live and work in lunar orbit. There are also discussions about Japanese astronauts eventually walking on the moon as part of Artemis missions. For Japan, this would be a historic moment, cementing its role as a full partner in human exploration. At the same time, Japan is developing its own advanced technologies that could play a role in future lunar bases. Robotics are a particular strength. In cooperation with Toyota, JAXA is working on a pressurized rover that could allow astronauts to travel long distances across the moon, while protected from its harsh environment. Japan's approach is careful and methodical. India's path to the moon has been different, but no less impressive. Through its space agency, ISRO, India has built a reputation for doing ambitious missions at relatively low cost. In 2008, India launched its first lunar mission, Chandrayaan-1. The spacecraft carried instruments from several countries and made one of the most important discoveries in modern lunar science. It found evidence of water molecules on the surface. This finding changed how scientists think about the moon and its potential resources, proving that even a relatively small mission could make a giant contribution. In 2019, India attempted its first landing with Chandrayaan-2. The orbiter worked well and continues to return valuable data, but the lander crashed during descent. For many nations, such a setback might have ended the effort. But India pressed on. In 2023, Chandrayaan-3 successfully landed near the moon's south pole, making India the first country to do so in that region. The lander and rover conducted experiments and confirmed India's growing expertise. The achievement was celebrated across the world and especially at home, where it became a symbol of national pride and technological progress. Officials have spoken about sending Indian astronauts, called Vyomanauts, to space aboard the nation's upcoming Gaganyaan program. While the first flights will be limited to Earth orbit, many believe India will eventually set its sights on the Moon. With a track record of achieving major goals on modest budgets, India's role in future lunar exploration could be surprisingly large. The growing importance of Japan and India on the lunar stage also reflects how exploration is changing. Smaller nations, working either independently or through partnerships, can take on meaningful roles. This makes the story of lunar exploration more global, more diverse, and less predictable. Japan and India both highlight different strengths. Japan focuses on cooperation, high-quality technology, and long-term strategy. India, meanwhile, emphasizes low-cost innovation and national drive. Its missions are not always perfect, but they push boundaries and prove what is possible, even without the massive funding of older space powers. Together, they show how the Moon is no longer just a stage for superpowers, but a destination that attracts the attention of nations all over the world. Private companies with lunar dreams. Increasingly, private companies are stepping forward with their own ambitions. Some are small startups, others are established giants in aerospace, but all of them see the Moon not only as a place of exploration, but also as an opportunity. Mining is one of the clearest areas where private firms see potential. The Moon's surface holds metals such as titanium and aluminum, which could one day be used for building habitats and machines. More importantly, it contains resources that are rare on Earth. Helium-3, for example, is often mentioned. Water is another valuable target. A firm could mine water, process it, and sell it to other spacefarers. Instead of rockets carrying every drop of propellant from Earth, they could refuel on the Moon. This would cut costs and make longer voyages, like missions to Mars, more realistic. Private companies see themselves as providers of this service. Tourism is another area where dreams are being shaped. While the first wave of visitors will certainly be astronauts and engineers, some firms imagine a future where wealthy travelers pay for the experience of standing on another world. Today, companies already sell tickets for suborbital trips and stays on private space stations. Extending that to the Moon is a natural next step in their marketing pitch. One can imagine luxury domes with panoramic windows looking out over the barren landscape, or even short excursions in pressurized rovers. Though these visions are far from reality, they are presented as part of the longer-term roadmap, giving investors and the public a sense of what might come. Infrastructure is another domain where business could change lunar exploration. Governments may lay the groundwork, but private industry often steps in to build the tools and systems needed to make things work efficiently. This could mean power grids made of solar panels scattered across the surface, communication networks linking landers and habitats, or construction systems that use lunar soil to print roads and buildings. Already, companies are experimenting with 3D printing technologies that might one day turn regolith into bricks or shelter walls. The commercial involvement in lunar projects is not limited to startups chasing big dreams. Established companies, some with long histories of building rockets or satellites, are actively part of the new wave. They see contracts from space agencies as a stepping stone. NASA's Artemis program, for instance, depends heavily on private partners to deliver cargo, landers, and even crew transport. This arrangement allows smaller firms to gain experience and credibility, while also opening the door to spin-off opportunities. Once a company proves it can deliver a payload to the Moon for NASA, it can offer the same service to other nations, universities, or even private buyers. This creates a marketplace rather than a single client system. Investors are watching carefully. The rise of space-focused venture capital shows how money is flowing into companies with lunar plans. Many of these investors understand that profits may not come quickly. It might take years, even decades, before large-scale mining or tourism becomes viable. But the potential payoff, both in financial terms and in global prestige, is enough to keep interest alive. Just as the early internet drew bold backers long before it turned into the giant economy we know today, so too does the space sector attract those willing to gamble on the future. There are legal and ethical questions tied to private lunar ventures. Who owns the moon or its resources? International treaties say no nation can claim sovereignty, but they are less clear about companies. Some laws in the United States and other countries now allow firms to claim ownership of resources they extract. Critics argue this could lead to conflicts or exploitation, while supporters say it provides the certainty needed for investment. The debate is ongoing, and the way it unfolds will shape how business is conducted beyond Earth. Another factor is collaboration versus competition. Some companies will compete fiercely, racing to be the first to offer certain services. Others may find cooperation more practical, especially in such a harsh and expensive environment. A network of firms might share infrastructure, pooling resources to reduce risk. For example, one company could provide power, another communications, and a third transportation. Together, they could support a larger human presence than anyone could achieve alone. There are also practical challenges that will test whether these business dreams can come true. Building machines that work reliably will not be easy. Transporting heavy equipment across the vast distance remains expensive, even with reusable rockets. And the timeline of returns on investment is long, something that does not always align with the expectations of shareholders. For all the excitement, many projects will likely fail before one or two succeed. But that is often how new industries grow. To some, the idea of profit-driven exploration might feel cold, as if the moon becomes just another site of extraction. To others, it is the only way to sustain a long-term presence. Government missions rise and fall with budgets and politics, but business tends to endure if there is money to be made. In this sense, private companies are bringing a different kind of permanence to lunar exploration. They want factories, depots, hotels, and networks. If even part of this vision comes true, the next century could see the moon transformed from a barren symbol of human daring into an active part of our economy and culture. That transformation, whether for better or worse, will be one of the most important stories of our time. Global governance of the moon. If many countries and companies start working on the moon, who decides what they can and cannot do? How do we prevent conflicts? How do we make sure that the resources are used fairly? These questions are not technical, they are political and legal, and they may prove harder to solve than the engineering challenges. The first attempt to answer them came during the Cold War. In 1967, the Outer Space Treaty was signed by the United States, the Soviet Union, and dozens of other nations. It remains the most important legal document about space. The treaty states that no nation can claim sovereignty over the moon or any other celestial body. It also bans the placement of nuclear weapons in space and says that space must be used for peaceful purposes. At the time, this treaty was a huge step forward. It prevented the moon from becoming the site of a new arms race. It also declared space as the province of all mankind, meaning it should belong to everyone, not just one nation. Yet the treaty left many questions unanswered. While it clearly bans national ownership of the moon, it does not explain what happens when private companies extract resources. Can a firm mine lunar ice and sell it? Or does that violate the idea that the moon belongs to all? For decades, this was a theoretical problem because no one had the technology or funding to attempt mining. But today, with private companies building lunar landers and governments planning permanent bases, the issue is becoming urgent. In the 1970s, there was another attempt to address these gaps. The Moon Agreement of 1979 declared that the moon and its resources were the common heritage of mankind, and that any benefits should be shared fairly among all nations. It also proposed an international regime to oversee the exploitation of resources. On paper, This agreement was stronger than the Outer Space Treaty. In practice, it failed. The United States, Russia, and China, along with most major spacefaring nations, never signed it. They saw it as limiting their freedom and feared it would force them to share too much with countries that had not invested in space exploration. As a result, the Moon Agreement has little power today. Only a handful of nations are part of it, none of them with major lunar programs. Because of this gap, many countries are now moving forward with their own laws and frameworks. The United States passed the Commercial Space Launch Competitiveness Act in 2015, which allows American companies to own and sell resources they extract from celestial bodies. Luxembourg, the United Arab Emirates, and Japan have passed similar laws, trying to position themselves as hubs for space mining companies. Critics argue that these national laws break the spirit of the Outer Space Treaty. Supporters say they are simply clarifying rights and encouraging investment. At the same time, new international efforts are emerging. The Artemis Accords are a set of principles for responsible exploration of the Moon and beyond. Countries that sign the accords agree to share data, protect heritage sites like the Apollo landing areas, and allow for the creation of safety zones around their operations to prevent interference. More than 30 nations have joined so far, but some major players, such as Russia and China, have refused. The idea of safety zones is one of the most debated parts of the Artemis Accords. Supporters see them as necessary. If two landers touch down close to each other and one's operations interfere with the other, conflict could arise. A safety zone is a way to avoid accidents. Critics worry that they are just another form of territorial claim, a way for countries to carve up parts of the Moon without saying so directly. The balance between protecting activities and avoiding de facto ownership is delicate, and it may define future legal battles. The Apollo landing sites are considered by many to be cultural treasures, like monuments on Earth. Should they be protected by international law, much like UNESCO protects World Heritage Sites? Or are they open to all, since no one owns the Moon? As more landers are sent, there is a risk that tracks, dust, or mining could damage these historic spots. Deciding how to protect them is as much a political question as it is a scientific one. Some nations argue that the Moon should be treated like the deep seabed or Antarctica, places that are not owned by anyone but managed through collective agreements. Others believe that nations and companies that invest heavily should be able to reap the rewards. Without agreement, tensions could rise. Imagine a scenario where two countries try to mine the same crater for ice. Who has the right to continue? Who decides what is fair? International organizations may play a role, but their power is limited. The United Nations Committee on the Peaceful Uses of Outer Space discusses these issues, but its decisions are slow and often require consensus among many members. By the time an agreement is reached, technology and politics may have already moved forward. Some experts suggest creating a new body specifically for lunar governance, similar to how the International Seabed Authority oversees mining in the oceans. Others believe informal agreements and bilateral deals may shape the future more than formal treaties. While the Outer Space Treaty bans weapons of mass destruction in space, it does not ban all military activity. Satellites already serve military purposes on Earth, and the Moon could someday be used for surveillance or communication systems. The line between peaceful use and military use is blurry. If one country places advanced sensors on the Moon, others may see it as a security threat, even if it is presented as a scientific tool. Managing these suspicions will require diplomacy and trust, something that is often in short supply. If companies dominate, the Moon could become a site of intense competition, where the strongest players control resources and weaker nations are left out. If international rules dominate, it could become a shared commons, but one that moves more slowly and cautiously. Both paths have supporters and critics. Ethical considerations are part of this debate as well. Should the Moon be preserved as a wilderness, untouched except for science? Or is it acceptable to reshape it into an industrial zone, Some argue that humanity has already damaged Earth and we should not repeat the same mistakes on another world. Others reply that the Moon is barren and lifeless, and its resources could help us avoid further damage on Earth. In the years ahead, the Moon will test our ability to cooperate as a species. It will show whether humanity can share a frontier without falling into the same patterns of rivalry that marked exploration on Earth. Each new project will add pressure to the system. Without clear rules, misunderstandings could escalate. With them, the Moon could become a place where nations find new ways to work together. Scientific revolutions on the Moon. The Moon is a treasure chest of knowledge waiting to be opened. Its soil, rocks, and hidden reserves preserve a record of cosmic history that Earth itself has largely erased. Its location, quiet and stable, makes it a perfect platform for instruments that cannot function well on our home planet. If the 21st century does succeed in building long-term bases on the Moon, the science that comes from them could change how humanity understands not just our own world, but the wider universe. One of the first revolutions will come from geology. Earth is an active planet, its surface constantly reshaped by erosion, volcanism, and tectonic motion. This means that rocks older than a few billion years are rare. The Moon, in contrast, has no atmosphere, no plate tectonics, and no liquid water flowing across its surface. Its ancient craters and highlands preserve a record stretching back more than 4 billion years. By drilling into the lunar crust and carefully studying its layers, geologists can reconstruct a timeline of impacts, eruptions, and surface changes that date back to the very dawn of the solar system. These findings would help answer questions about when planets formed, how often large impacts occurred, and what role those impacts played in shaping Earth's early environment. Another breakthrough may come from studying the so-called late heavy bombardment, a period roughly 3.9 billion years ago when many large impacts struck the Moon. The evidence for this comes from the Apollo samples, but those samples were limited to a few regions. With new missions, scientists could collect material from across the Moon, giving a clearer picture of whether that bombardment truly happened everywhere, or if it was more localized. This matters because the same impacts that scarred the Moon would also have struck Earth, possibly influencing the origins of life. By reading the Moon's rocks, scientists could gain insight into whether life on Earth arose in the shadow of cosmic violence, or in a calmer setting than once imagined. The Moon's surface also holds records of the solar wind. With no atmosphere to protect it, particles from the Sun have been embedding themselves into the lunar soil for billions of years. These trapped particles act like a history book of solar activity, recording changes in the Sun's behavior over immense spans of time. By analyzing these records, scientists could learn about the evolution of the Sun, its cycles, and its role in shaping the environments of Earth and the other planets. This could also improve our understanding of space weather, which is critical for protecting satellites and electrical systems back home. On Earth, radio signals from cities, satellites, and natural activity fill the skies with noise. The far side of the Moon is permanently shielded from Earth's radio emissions. It is perhaps the quietest place in the inner solar system for listening to the universe. Astronomers have long dreamed of building a giant radio telescope there, perhaps spread across a crater, to study signals from the early universe. Such an instrument could detect faint radio waves from the cosmic dark ages, the period after the Big Bang, but before the first stars lit up. No Earth-based telescope can do this because our own radio noise drowns out the signals. A lunar observatory might reveal how the first galaxies formed and how the universe's large-scale structure began to take shape. Optical and infrared astronomy would also benefit. Telescopes on Earth's surface must peer through the atmosphere, which distorts light and blocks many wavelengths. The Moon has no such barrier. A telescope placed on its surface could operate with unmatched clarity, capturing views of distant galaxies, stars, and planetary systems. While the James Webb Space Telescope orbits in deep space, instruments on the Moon would be more accessible for repair, expansion, and long-term operation. In addition, the extreme cold of shadowed craters could serve as natural cooling systems for infrared detectors. reducing the need for complex technology. This could allow for telescopes larger and more sensitive than anything we have now. When large asteroids struck Earth billions of years ago, debris would have been ejected into space, some of which likely landed on the Moon. Unlike Earth, where such rocks would have been destroyed by erosion and recycling, they may still lie in lunar soil, waiting to be found. Discovering and analyzing these pieces could tell us about the earliest conditions on Earth, long before the oldest surviving rocks on our planet. The Moon is also an ideal laboratory for studying how life reacts to alien conditions. Long-term bases could carry plants, microbes, and perhaps even small ecosystems to see how they adapt to low gravity, high radiation, and constant dust. Understanding how biology can endure lunar conditions would help scientists develop systems for food production, medicine, and long-term survival in space. Some theorists suggest that experiments requiring extreme stability could be carried out more effectively on the Moon than on Earth. Gravitational wave detectors, for instance, might operate better on the Moon's surface, where seismic noise is minimal compared to Earth's constant rumbling. These detectors could join existing space-based and ground-based observatories to form a network capable of studying the most violent events in the cosmos, collisions of black holes, mergers of neutron stars, and perhaps signals from the earliest moments after the Big Bang. The Moon may become a place to test new systems for measuring time and space with extreme precision, using atomic clocks and laser instruments unaffected by Earth's atmosphere. Such tools would not only advance physics, but also support navigation for future spacecraft traveling throughout the solar system. Perhaps most exciting is that science on the Moon is not limited to what we already imagine. Every time humans open a new frontier, unexpected discoveries follow. Just as Apollo samples revealed mysteries no one had predicted, like the high levels of titanium in some lunar rocks, future missions may uncover surprises that rewrite textbooks. There may be chemical processes unknown on Earth, minerals formed under conditions we cannot reproduce here, or signals from the cosmos preserved in ways we have never seen. The Moon is a time capsule of the solar system, and unlocking it may reveal things we do not yet know how to ask. Just as Antarctica became a continent of science, the Moon may become humanity's first great scientific outpost beyond our planet. Its barren surface could turn out to be one of the richest fields of knowledge we have ever explored. The Moon, in 2050, a shared human outpost. By the middle of the 21st century, the Moon could be a place where humanity has carved out a permanent presence, a shared outpost that belongs to no single nation, but to all who have worked to make it possible. The year 2050 is far enough away to allow for imagination, yet close enough that most alive today would live to see it. In 2050, the idea of astronauts staying for months at a time might be normal. Habitats could be buried beneath lunar soil to protect from radiation, with greenhouses providing fresh food and oxygen. Solar farms near the poles could supply power, while mining facilities extract resources to sustain life and fuel spacecraft. There could be entire clusters of activity, buzzing with machines, research labs, and humans going about daily routines. Science would likely remain the driving purpose. The Moon in 2050 would be a laboratory for understanding the cosmos. Industry would also take root. The Moon's resources could support construction, fuel production, and perhaps even rare materials for use on Earth. Mining companies might be in the opening stages of operating robotic fleets that dig into regolith and harvest various resources. Helium-3, though still uncertain as an energy source, may remain a target of research and investment. By then, factories might exist on the Moon that build components for spacecraft, taking advantage of lower gravity to reduce launch costs. American, European, Chinese, Indian, Japanese, Russian, and private missions may all maintain their own facilities, yet depend on each other for trade, emergency support, and shared infrastructure. Astronauts might travel between bases, much like scientists move between research stations in Antarctica. Despite rivalries, the practical realities of surviving in such a harsh environment could encourage collaboration. Life on the Moon by 2050 would not be easy, but it could become routine. Children growing up on Earth could watch live broadcasts of lunar sunrises. A new culture might develop among lunar settlers, shaped by the experience of living in constant danger, yet relying on one another in ways Earth rarely demands. By 2050, reusable lunar landers and cargo shuttles could make the trip regular and relatively cheap compared to today. A steady flow of materials, equipment and travelers might move between the two worlds, creating something like an Earth-Moon highway. Lunar orbit stations could act as hubs, coordinating traffic and logistics. With this network in place, the Moon would feel part of a connected system, the first link in humanity's expansion across the solar system. For generations, the Moon has been a reminder of what humanity once achieved and then lost. By 2050, it could stand instead as proof that humanity can commit to something larger than politics or short-term goals. The bases, observatories and mining facilities might be celebrated not only for their practical value, but for what they represent. A species learning to live beyond its cradle. The Moon's landscape may be dotted with human lights glowing against the darkness, visible even from Earth with strong telescopes. Craters that once lay untouched for eons might host power stations and domes. The silence of the lunar surface could be broken by the hum of machinery and the footsteps of settlers. To those living in that future, it may not seem extraordinary. It may simply be part of life, much like airplanes, satellites, and the internet became ordinary for earlier generations. The leap from Earth to space would have become not a one-time stunt, but a lasting way of life. And on that uplifting note, this video must come to an end. Comment down below if you'd like a similar video for Mars. And if you enjoyed this, consider leaving a like and subscribing. Thanks for watching.